Hello there, curious soul. I'm so glad you found your way here tonight. We're going to embark on perhaps the most profound journey humans have ever attempted, on tracing the very first moments of everything that exists. Tonight, we're asking the question that has haunted philosophers and physicists alike. How did the universe begin? How did it truly spring from nothing? Or is there something more mysterious at play? Before we begin, I'm genuinely curious. Where are you listening from right now? And what time is it where you are? I love imagining all the different corners of the world where these words might find you. If you find yourself enjoying this gentle exploration of cosmic mysteries, please do consider giving this video a thumbs up. It helps others discover this quiet corner of the internet where we can wonder together. Here's something delightfully absurd. I'm convinced that the universe began specifically to create the perfect conditions for making hot chocolate. Everything else, stars, galaxies, life itself, is just elaborate cosmic engineering to ensure cocoa beans and milk could eventually meet in a warm mug. So settle in, dear listener. Let your breathing slow, your shoulders drop. Tonight, we're traveling back to the very beginning of time itself, to a moment so strange and beautiful that it challenges everything we think we know about reality. There's something about the deep night sky that makes philosophers of us all. You've felt it, haven't you? That moment when you step outside under a canopy of stars and suddenly feel very small and very curious all at once. Your mind begins to wander backward through time, past your childhood, past your grandparents' stories, past recorded history, past the formation of Earth itself. And then you hit that wall, that moment when your imagination reaches for something beyond reach, the very beginning of everything.
How did it all start?
What was there before the first star ignited, before the first galaxy formed, before space itself existed? Before the first galaxy formed, before space itself existed? Children ask this question with such natural ease. Mommy, what was there before everything? And we adults fumble for answers, realizing that this simple question from a 5-year-old has stumped the greatest minds in human history. It's beautiful, really, how children intuitively grasp that this is the question, the one that matters most. Scientists have been grappling with this cosmic mystery for centuries, and what they've discovered is both more wonderful and more strange than any creation story ever told. The universe, it seems, has a birthday about 13.8 billion years ago. Everything we know, every atom in your body, every star in the sky, space itself and time itself, began. But here's where it gets deliciously complicated. When we say began, we're not talking about something exploding into empty space. We're talking about space itself coming into existence, time itself starting to tick. It's like trying to imagine what's north of the North Pole, so our usual ways of thinking simply don't apply. The ancient Greeks wondered about this too. They had a word, ex nihilo, meaning out of nothing, but they couldn't quite wrap their minds around it either. How does something come from nothing? It seems to violate our most basic intuitions about how the world works. And yet here we are, you and I, made of star stuff, having this conversation across the cosmos through invisible waves of light and electricity. We exist, and that existence had to begin somewhere, somehow. The very fact that you're listening to these words is proof that the universe solved this impossible puzzle of creation. What's particularly enchanting is that modern physics has revealed that our intuitions about nothing are completely wrong. The deepest, emptiest space we can imagine is actually buzzing with activity, pregnant with possibility. The quantum realm has shown us that nothingness isn't empty at all. It's full of potential, like a cosmic womb waiting to give birth to reality. So as we begin this journey together, let's hold our question lightly, not as a problem to be solved, but as a mystery to be wondered at, because sometimes the most profound truths aren't found in answers, but in the quality of our questions themselves. When you think of nothing, what comes to mind? Perhaps an empty room, or the space between stars, or maybe just, nothing at all. But here's where our cosmic detective story takes its first surprising turn. The nothing that physicists talk about is unlike anything you've ever imagined. Let me paint you a picture. Imagine you could remove everything from a region of space, every atom, every particle, every bit of light. You might think you'd have perfect nothingness, but quantum mechanics whispers a different story. Even in this most empty space, something extraordinary is happening. The quantum vacuum, as physicists call it, is like a calm ocean that appears still on the surface, but is actually teeming with invisible currents underneath. Virtual particles are constantly popping into existence and vanishing again, like fireflies blinking in and out of visibility. These aren't just theoretical curiosities. They have real, measurable effects on the world around us. Consider the Casimir effect, discovered by Dutch physicist Hendrik Casimir. When you place two perfectly smooth metal plates very close together in a vacuum, they actually attract each other. Why? Because the virtual particles in the quantum vacuum create a tiny pressure difference. It's as if the emptiness itself is gently pushing the plates together. This revolutionizes our understanding of nothingness. The vacuum isn't empty. It's the lowest energy state that space can have while still obeying the laws of quantum mechanics. It's pregnant with possibility, humming with potential energy that can, under the right circumstances, bloom into actual particles and forces. Think of it like a perfectly calm lake. From above, it looks serene and empty, but dive below the surface, and you discover it's full of currents and life and movement. The quantum vacuum is reality's version of that deceptively calm lake. This has profound implications for how the universe might have begun. If nothingness isn't really nothing, then perhaps something emerging from nothing isn't as paradoxical as it seems. Maybe the universe didn't violate any laws. Maybe it simply took advantage of the creative potential that was always there in the quantum foam. The ancient philosophers had an axiom: ex nihilo nihil fit. Nothing comes from nothing. But quantum mechanics suggests they were working with an incomplete definition of nothing. The nothing that physicists study is rich with mathematical structure, governed by laws, full of symmetries and possibilities. It's like discovering that what you thought was an empty stage is actually set for a play. The curtain hasn't risen yet, the actors haven't appeared, but the stage is there, the lights are ready, and the script exists in the quantum laws that govern reality. Werner Heisenberg, one of the founders of quantum mechanics, once said that what we observe is not nature itself, but nature exposed to our method of questioning. Perhaps the same is true of nothingness. The deeper we look, the more we discover that our questions themselves shape what we find. So when cosmologists talk about the universe emerging from nothing, they're not talking about the nothing of common sense, the absence of anything at all. They're talking about the quantum vacuum, a nothing that is paradoxically full of potential, a silence that contains all possible songs. Imagine if you could see a photograph of yourself from the moment you were born, not just any baby picture, but an image captured in the very instant you took your first breath. That's essentially what cosmologists have found when they look at the cosmic microwave background radiation, the universe's very first baby picture. This ancient light has been traveling through space for nearly 13.8 billion years, carrying with it the story of how everything began. When you tune an old television to a channel with no signal, about 1% of that static you see is actually this cosmic background radiation, the afterglow of creation itself, flickering on your screen. But let's step back to understand how this cosmic baby picture came to be. In the universe's earliest moments, everything was incredibly hot and dense. Matter and energy were so tightly packed together that light couldn't travel freely. It would bounce off particles almost immediately, like trying to shine a flashlight through thick fog. For about 380,000 years, the universe was essentially opaque. Light existed, but it was trapped, constantly scattering off the soup of particles that filled all of space. Then something beautiful happened. As the universe expanded and cooled, it reached a temperature where electrons and protons could finally combine to form neutral hydrogen atoms. This moment is called recombination, and it was like the cosmic fog suddenly clearing. For the first time, light could travel freely through space. The universe became transparent, and that first flash of free light has been traveling toward us ever since, cooling and stretching as space itself expanded. When we detect this cosmic microwave background today, we're essentially looking back in time to see the universe as it was when it was just a baby, only 380,000 years old, which is practically newborn in cosmic terms. It's like having a time machine that lets us witness the moment when the universe first became clear and bright. What's remarkable is how uniform this background radiation is. No matter which direction we look in the sky, the temperature is almost exactly the same, just about 2.7 degrees above absolute zero. This tells us something profound about the early universe. It was incredibly smooth and homogeneous. But almost exactly the same is the key phrase here. There are tiny variations in temperature, neversince of just a few millionths of a degree, but per the individual into mu. These minute fluctuations are like the universe's fingerprints, revealing the quantum fluctuations that would eventually grow into the galaxies and stars we see today. It's poetry written in physics. Those tiny ripples in the cosmic microwave background are the seeds from which all cosmic structure grew. The slight density variations they represent eventually collapsed under their own gravity to form the first stars, the first galaxies, and ultimately the solar system where you and I exist today. The Planck satellite, launched by the European Space Agency, has mapped these temperature variations with exquisite precision. The resulting images look like abstract art, much swirling patterns of slightly warmer and cooler regions painted across the entire sky. But these beautiful patterns are actually the most important data we have about the universe's infancy. Looking at the cosmic microwave background is like being an archaeologist of time itself. Each subtle variation tells us about the conditions that existed when the universe was younger than a human lifetime. We can read in these patterns the story of how quantum fluctuations in the early universe eventually gave rise to the rich tapestry of cosmic structure we see today. There's something deeply moving about the fact that this ancient light surrounds us, always. Right now, as you listen to these words, you're bathed in the afterglow of creation. These photons have been traveling since before the Earth formed, before the sun ignited, before our galaxy took its spiral shape. And in a sense, by detecting and studying this cosmic microwave background, we're not just learning about the universe's past and we're participating in its story. We're the universe looking back at its own baby pictures, consciousness emerging from cosmos and turning to contemplate its own origins. The name Big Bang is perhaps the most misleading term in all of science. It conjures images of a massive explosion, like a cosmic bomb going off in empty space, sending matter and energy flying outward in all directions. But the reality is far more subtle and strange than any explosion you could imagine. The term was actually coined by astronomer Fred Hoyle in 1949, and he meant it as a dismissive joke. Hoyle favored the steady-state theory, the idea that the universe had always existed and was constantly creating new matter to maintain its density as it expanded. He thought the idea of a cosmic beginning was ridiculous, so he sarcastically called it the Big Bang during a BBC radio broadcast. Ironically, the name stuck, even though it completely misrepresents what actually happened. There was no bang. There was no explosion. There wasn't even a where for an explosion to happen in, because space itself was being created in the process. Instead, imagine the universe as a balloon being inflated. As it expands, every point on the balloon's surface moves away from every other point. There's no center to the expansion, no single point where the balloon started growing. Every point can claim to be the center, because from any point's perspective, everything else is moving away. This is what happened with space itself in the early universe. It wasn't that matter exploded outward into pre-existing empty space. Rather, space itself was expanding, carrying matter along with it. The expansion wasn't happening in space. It was the expansion of space. Picture this. You're an ant on that balloon as it's being inflated. From your perspective, every other ant on the balloon is moving away from you, and the farther away they are, the faster they seem to be receding. But none of the ants are actually moving across the balloon's surface. And it's like either they're all just being carried along by the expansion of the balloon itself. This is exactly what we observe in our universe today. Distant galaxies are moving away from us, and the more distant they are, the faster they're receding. This relationship, called Hubble's law, is one of the key pieces of evidence for the Big Bang theory. But here's where it gets even more mind-bending. If we trace this expansion backward in time, we find that the universe becomes smaller and smaller, denser and denser, hotter and hotter. Eventually, we reach a point where our physics breaks down Minerva, a moment when the universe was compressed into a space smaller than a proton, where temperatures and densities become literally infinite. This is called the initial singularity. And it's not really a place or a time in any conventional sense. It's more like a boundary endery, the edge of what our current understanding of physics can describe. It's where the equations of general relativity throw up their hands and say, I don't know what happens here. What makes this even more puzzling is that the Big Bang wasn't an explosion that happened at a particular location. It happened everywhere at once. Every point in space was once compressed into that initial singularity. The spot where you're sitting right now was once part of that incomprehensibly dense, hot beginning. It's like trying to imagine what the number line looked like before numbers existed. The question doesn't quite make sense, because you're trying to apply concepts that only exist after the thing you're asking about has already happened. The expansion that began with the Big Bang is still happening today. Space is still growing, carrying galaxies away from each other like raisins in a rising loaf of bread. But unlike an explosion, which slows down over time due to friction and gravity, the expansion of space itself can actually accelerate. And we've discovered that it is accelerating, driven by the mysterious force we call dark energy. So when we talk about the Big Bang, we're not describing a moment when something exploded. We're describing the moment when space and time themselves began to exist, when the laws of physics as we know them first became meaningful, when the universe transitioned from a state so extreme that we can barely conceive of it to something we can begin to understand. It's a birth, not an explosion, a gentle unfolding, not a violent blast. The universe didn't begin with a bang, Mitz. It began with a whisper, a quantum fluctuation that somehow became everything we know and love. Here's a question that might make your brain feel slightly wobbly. What happened before the Big Bang? It's natural to ask this, mine. After all, we're accustomed to thinking of time as an endless river flowing from past to future. But the Big Bang challenges our most basic assumptions about the nature of time itself. According to our best current understanding, time didn't exist before the Big Bang. This isn't just a case of not knowing what happened earlier. Nearer, it's that earlier doesn't have any meaning. Time itself began with the universe. It's like asking what's north of the North Pole. The question assumes a framework that doesn't actually exist. This concept was first seriously proposed by Augustine of Hippo in the 4th century, long before modern cosmology. When asked what God was doing before creating the world, Augustine cleverly replied that there was no before, because time itself was created along with the world. Modern physics has essentially confirmed this ancient insight. Einstein's theory of relativity showed us that time isn't the absolute universal constant we once thought it was. Time can slow down or speed up depending on gravity and motion. Near a black hole, time crawls. On a speeding spaceship, time dilates. What we call now isn't the same everywhere in the universe. Just there's no universal clock keeping cosmic time. But the Big Bang takes this even further. If space and time are woven together into what Einstein called space-time, then the birth of space necessarily means the birth of time. If before the Big Bang, there was no before, because there was no time for a before to exist in. This creates a beautiful paradox for our minds to contemplate. We're used to thinking causally, A happens, then B happens, then C happens. But at the moment of the Big Bang, causality itself begins. The universe doesn't have a cause in the traditional sense, because causes require time, and time begins with the universe. It's like being asked to play a song before music was invented. The question contains assumptions that don't apply to the situation it's asking about. The universe didn't begin at a particular moment in time. It began along with time itself. Consider what this means for our understanding of existence. Everything you've ever experienced, every moment of your life, every tick of every clock, exists within this bubble of time that began 13.8 billion years ago. The present moment you're experiencing right now is part of this cosmic unfolding that started with the Big Bang. Some physicists have proposed that time might be cyclical, that our universe could eventually collapse back into a big crunch, which could then trigger another Big Bang, creating an endless cycle of cosmic death and rebirth. In this model, time would be like a cosmic heartbeat, expanding and contracting eternally. Others suggest that time might branch like a tree, with our universe being just one branch among many in a vast multiverse. Each branch would have its own timeline, its own history, its own unique unfolding of events. But perhaps the most mind-bending possibility is that time itself might be an emergent property, something that arises from more fundamental processes, like wetness emerges from water molecules, or consciousness emerges from neurons. In this view, time isn't fundamental to reality, but rather a consequence of the way information is processed in complex systems. The physicist Carlo Rovelli has proposed that time might not exist at a fundamental level at all. Instead, what we experience as the flow of time might be a result of our perspective as complex, information-processing beings embedded in a universe that's fundamentally timeless. These ideas challenge our most basic intuitions about reality. We feel the passage of time so intimately, Seva way, the beating of our hearts, the rhythm of our breathing, the memories of our past and hopes for our future. Yet physics suggests that this felt experience of temporal flow might be an illusion, a consequence of our limited perspective within a reality that's far stranger than we can easily imagine. What's beautiful about this mystery is that it connects the most abstract concepts in physics with the most personal aspects of human experience. When we ask about the beginning of time, we're not just asking about cosmic origins, we're asking about the nature of existence itself, about what it means to be conscious beings embedded in a universe that somehow created the conditions for consciousness to emerge. So when we say the universe began 13.8 billion years ago, we're not just dating an event, we're marking the moment when the very possibility of events began, when time itself started its eternal dance, when the cosmic clock began to tick. In the first fraction of a second after the Big Bang more, we're talking about a period so brief that it makes a blink of an eye seem like an eternity, with something absolutely extraordinary happened. The universe underwent a period of expansion so rapid and dramatic that it defies our everyday understanding of how things can change. This period is called cosmic inflation, and it lasted for somewhere between 10 circumflex 36 and 10 circumflex 32 seconds. During this incomprehensibly brief moment, the universe expanded by a factor of at least 10 circumflex 26. That's a 1 followed by 26 zeros. To put this in perspective, imagine a grain of sand suddenly becoming larger than our solar system. That's the kind of expansion we're talking about. But here's the truly mind-bending part. This expansion happened faster than the speed of light. Now, before you think physics has gone completely mad, remember that nothing can travel through space faster than light. But space itself can expand at any rate it pleases. It's like being on a treadmill that's accelerating faster than you can run. You're not breaking any speed limits, but you're still moving backward relative to the room around you. The idea of cosmic inflation was proposed by physicist Alan Guth in 1980, and it solved several puzzling problems about the universe we observe today. Before inflation theory, cosmologists faced what they called the flatness problem and the horizon problem, technical names for some very strange observations about our universe. The flatness problem is this: when we measure the geometry of space, we find it's remarkably flat, not curved like a sphere or saddle-shaped like a hyperbolic surface, but flat like a perfectly smooth sheet of paper. This is surprising because, according to general relativity, space should be curved by the matter and energy it contains. For space to be as flat as we observe, the density of matter and energy in the universe has to be tuned to an incredibly precise value. The horizon problem is equally puzzling. When we look at the cosmic microwave background radiation from opposite sides of the sky, we find that these regions have almost exactly the same temperature. But according to standard Big Bang theory, These regions should never have been in contact with each other. They're too far apart for light to have traveled between them in the time since the Big Bang. Cosmic inflation elegantly solves both problems. The rapid expansion stretched space so dramatically that regions that were once close together and in thermal equilibrium were suddenly separated by vast distances. This explains why the cosmic microwave background looks so uniform and sere. It's the stretched-out echo of what was once a small, uniform region. The inflation also explains the flatness of space. Just as the surface of a balloon appears flat to an ant, if the balloon is inflated to enormous size, the inflation of the universe stretched space so much that even if it started with significant curvature, it would appear flat to us today. But what could have caused such dramatic expansion? The answer lies in a hypothetical field called the inflaton field minus, a kind of energy that fills all of space and has the strange property of creating gravitational repulsion rather than attraction. Unlike normal matter, which causes space to curve inward, the inflaton field causes space to expand outward. Think of it like a cosmic spring that's been compressed and suddenly released. But instead of pushing matter apart, it pushes space itself apart, carrying everything along with it. The energy for this expansion comes from the inflaton field itself, which eventually decays into the matter and radiation that would go on to form stars and galaxies. This decay marks the end of inflation and the beginning of what we might call the ordinary Big Bang period, the period when the universe continued expanding, but at a much more sedate pace, allowing matter and energy to cool and begin forming the structures we see today. What's particularly elegant about inflation theory is that it makes specific predictions about what we should observe in the cosmic microwave background. The tiny quantum fluctuations in the inflaton field should have left their imprint on the distribution of matter and energy in the early universe, creating the pattern of hot and cold spots we observe today. These fluctuations are like the universe's fingerprints, unique patterns that tell us about the quantum processes that were happening during inflation. When we map the cosmic microwave background with exquisite precision, we're essentially reading the quantum signature of the inflaton field from nearly 14 billion years ago. The theory of cosmic inflation transforms our understanding of the Big Bang from a singular event into a phase transition, a moment when the universe shifted from one state to another, like water suddenly freezing into ice or steam suddenly condensing into droplets. It suggests that the universe we can observe might be just a tiny fraction of a much larger reality that was created during inflation. Beyond our cosmic horizon, there might be regions of space that underwent different amounts of inflation, creating a vast cosmic landscape of which our observable universe is just one small patch. Step into the quantum world, and you'll discover that what we call empty space is actually the universe's most elaborate dance floor. Here, in the seemingly vacant regions between atoms, between planets, between galaxies, an invisible ballet is constantly unfolding, a choreography of particles that appear and disappear like ghosts in the cosmic machinery. These are called virtual particles, and they're perhaps the most enchanting characters in the quantum story. Unlike the particles we're familiar with, Myth's electrons, protons, photons, virtual particles, exist in a state of perpetual maybe. They pop into existence as particle pairs, dance together for an infinitesimally brief moment, then annihilate each other and vanish back into the quantum foam. Imagine you're watching a perfectly still pond. To your eyes, it appears calm and empty. But if you could see at the molecular level, you'd discover that the water is actually in constant motion, molecules bouncing and vibrating, creating tiny ripples and currents that are invisible to normal observation. The quantum vacuum is like that pond, appearing empty to our instruments, but seething with activity at the smallest scales. These virtual particles aren't just theoretical curiosities. They have real, measurable effects on the world around us. They're responsible for the Casimir effect, where two metal plates placed very close together in a vacuum experience a slight attractive force. They contribute to the magnetic moment of electrons, making our most precise measurements of quantum mechanics possible. They even play a role in the evaporation of black holes through Hawking radiation. But here's where it gets truly magical. These virtual particles are borrowing energy from the universe itself. According to Heisenberg's uncertainty principle, energy and time are linked in such a way that the universe can lend energy for very short periods. The more energy borrowed, the shorter the time it can be kept. It's like having a cosmic bank account that allows infinite overdrafts, but only for microseconds. A virtual particle pair can borrow enough energy to exist, but they have to pay it back so quickly that they annihilate before anyone can catch them in the act. They're quantum embezzlers, stealing energy from the vacuum and immediately returning it before the universe's accounting system notices. This quantum borrowing creates what physicists call zero-point energy, the lowest possible energy that a quantum system can have. Even at absolute zero temperature, when all thermal motion stops, quantum systems still have this irreducible minimum energy. It's as if the universe has a built-in restlessness, an inability to be completely still. The implications are profound. If empty space is actually full of virtual particles popping in and out of existence, then the boundary between something and nothing becomes beautifully blurred. The quantum vacuum isn't empty, it's pregnant with potential, a cosmic womb where reality is constantly being born and reborn. Some of these virtual particles occasionally become real through a process called pair production. When a high-energy photon passes through a strong electric field, it can convert into a particle-antiparticle pair. The virtual becomes actual, the potential becomes manifest. Some of these virtual particles occasionally becomes manifest. It's like the universe's magic trick, pulling real particles out of the apparent emptiness of space. This quantum choreography extends throughout the universe. Right now, as you listen to these words, virtual particles are appearing and disappearing in the space around you, in the air you breathe, in the atoms of your body. You're immersed in this quantum dance, surrounded by the universe's constant creativity. The physicist John Wheeler once described the quantum vacuum as the most stiff and solid thing in the universe, despite appearing empty. It's stiff because it resists changes to its energy state, and solid because it fills all of space uniformly. Yet it's also the most dynamic and creative aspect of reality, constantly generating new possibilities. What's particularly beautiful is that these virtual particles connect quantum mechanics to cosmology. The same quantum fluctuations that create virtual particles in empty space may have been responsible for the initial seeds that grew into galaxies and stars. The tiny energy fluctuations in the quantum vacuum during cosmic inflation may have been stretched and amplified to create the large-scale structure of the universe we observe today. In this view, the cosmic microwave background, that ancient light from the early universe, carries the signature of quantum fluctuations that occurred when the universe was smaller than a proton. The patterns we see in the sky today are the fossilized remains of virtual particles that existed in the first fraction of a second after the Big Bang. So the next time you look up at the night sky, remember that you're not looking at empty space, punctuated by stars. You're looking at a quantum ocean, alive with invisible activity, where the universe is constantly creating and destroying possibilities, where the boundary between existence and non-existence is as fluid as water, as mysterious as a dance performed in darkness. There's a fundamental fuzziness built into the fabric of reality, a cosmic uncertainty that makes the universe far more interesting than it would be if everything were perfectly predictable. This is Heisenberg's uncertainty principle, and it's not just a limitation of our measuring instruments per se. It's a deep truth about the nature of existence itself. Werner Heisenberg discovered this principle in 1927 while working on the mathematics of quantum mechanics. What he found was that certain pairs of properties, like position and momentum, or energy and time, cannot be measured simultaneously with perfect precision. The more precisely you know one, the less precisely you can know the other. But here's the beautiful part. This uncertainty isn't a bug in the universe's operating system. It's a feature. The uncertainty principle is what allows the universe to be creative, to generate new possibilities, to pull energy out of apparently empty space and create something from nothing. Think of it this way. If you could measure both the position and momentum of every particle in the universe with perfect precision, you could predict the future with absolute certainty. The universe would be a giant clockwork mechanism, ticking away predictably through eternity. But the uncertainty principle ensures that there's always a fundamental element of surprise built into reality. This uncertainty manifests most dramatically in the relationship between energy and time. The principle tells us that for very short periods, the universe can borrow energy from nowhere as long as it pays the energy back quickly enough. The shorter the time period, the more energy can be borrowed. It's like having a cosmic credit card with an infinite limit. But the bill comes due almost instantly. Virtual particles can borrow enough energy to exist, but they have to annihilate and return the energy before the universe's accounting system catches up with them. They're living on borrowed time in the most literal sense possible. This energy borrowing happens constantly throughout the universe. Even in the emptiest regions of space, particle pairs are popping into existence, dancing their brief dance and disappearing again. The quantum vacuum is like a bustling marketplace, where energy is constantly being borrowed and repaid in transactions that happen faster than anything we can directly observe. But sometimes, these borrowed particles escape their debt. Near the event horizon of a black hole, one particle from a virtual pair might fall in while the other escapes. The escaped particle becomes real, carrying away energy from the black hole. This is the mechanism behind Hawking radiation, the process by which black holes slowly evaporate over time. The uncertainty principle also explains why atoms don't collapse. In classical physics, electrons should spiral into the nucleus, radiating energy as they fall. But quantum uncertainty prevents this catastrophe. The electron can't be pinned down to a precise position and momentum simultaneously. This quantum fuzziness is literally what makes chemistry possible. The shapes of molecules, the bonds between atoms, the complex dance of electrons that allows life to exist. All of this emerges from the fundamental uncertainty that prevents electrons from behaving like tiny planets orbiting atomic suns. On a cosmic scale, the uncertainty principle may have played a crucial role in the birth of the universe itself. During the period of cosmic inflation, quantum fluctuations in the inflaton field created tiny variations in density. These variations were then stretched and amplified by the rapid expansion of space, eventually growing into the galaxies and large-scale structures we see today. In this view, the uncertainty principle is the universe's creative engine. Without it, the early universe would have been perfectly uniform, and no structures would have formed, no stars, no planets, no life. The cosmic microwave background would show a perfectly smooth temperature distribution, instead of the subtle patterns that reveal the quantum origins of cosmic structure. The uncertainty principle also has profound implications for the nature of measurement and observation. When we measure a quantum system, we're not just passively recording information, we're actively participating in the creation of reality. The act of measurement forces the universe to choose a specific value from a range of possibilities. This has led to some of the deepest philosophical questions in physics. If reality is fundamentally uncertain until observed, what does that tell us about the nature of existence? Are we co-creators of reality, or are we simply revealing aspects of reality that were always there but hidden from view? Some interpretations of quantum mechanics suggest that every measurement creates a branching of reality, with each possible outcome occurring in a separate universe. In this view, the uncertainty principle isn't just allowing the universe to be creative, it's constantly creating new universes, an infinite branching tree of possibilities. Whether or not you subscribe to such radical interpretations, the uncertainty principle reminds us that the universe is far stranger and more wonderful than our classical intuitions suggest. It's a reality where precision is impossible, where creativity is built into the laws of physics, where the very act of trying to pin down the universe reveals its fundamentally elusive nature. In the end, Heisenberg's uncertainty principle is perhaps the universe's way of maintaining its sense of mystery, ensuring that no matter how much we learn, there will always be something left to wonder about. The ghostly dance of virtual particles might seem like abstract physics, removed from the tangible world we experience every day. But these ephemeral quantum fluctuations have surprisingly real consequences that ripple through the cosmos, affecting everything from the behavior of atoms to the fate of black holes. Let's start with something you can actually observe in a laboratory. Take two perfectly clean, perfectly flat metal plates and place them parallel to each other in a vacuum, separated by a distance smaller than the width of a human hair. According to classical physics, nothing should happen. After all, there's nothing between the plates but empty space. But quantum mechanics tells a different story. All the virtual particles that constantly appear and disappear in the quantum vacuum create what's called zero-point energy. Between the plates, only virtual particles with wavelengths smaller than the gap can exist. Outside the plates, virtual particles of all wavelengths are possible. This creates a pressure difference. Literally, the vacuum outside the plates pushes them together. This is the Casimir effect, and it's been measured with exquisite precision. It's not just a curiosity of quantum mechanics. It's a real force that engineers have to account for when designing micro-scale devices. In the world of nanotechnology, where components are separated by distances comparable to the wavelength of light, the Casimir effect can be stronger than gravity. But virtual particles don't just push metal plates together, they also contribute to one of the most precisely measured quantities in all of physics, into the magnetic moment of the electron. When physicists calculate this quantity using quantum field theory, they have to include the effects of virtual particles that briefly surround every electron like a ghostly cloud. These virtual particles subtly alter the electron's magnetic properties in ways that can be measured to incredible precision. It's like measuring the distance from New York to Los Angeles and being accurate to within the width of a human hair. This extraordinary agreement between theory and experiment is one of the greatest triumphs of quantum mechanics. It shows that virtual particles, despite their ephemeral nature, have measurable effects on the fundamental properties of matter. The consequences extend far beyond laboratory experiments. Virtual particles play a crucial role in the structure of atoms themselves. The electromagnetic force that holds atoms together is mediated by virtual photons, mind particles of light that carry force between charged particles. When an electron and proton attract each other in a hydrogen atom, they're actually exchanging virtual photons in a quantum handshake that creates the chemical bond. Even more dramatically, virtual particles are responsible for the slow death of black holes. Stephen Hawking showed that near the event horizon of a black hole, virtual particle pairs can be separated by the extreme gravitational field. One particle falls into the black hole while the other escapes, carrying away energy. From the outside, it appears that the black hole is radiating particles and slowly evaporating. This Hawking radiation is incredibly faint for stellar mass black holes, and a black hole with the mass of our Sun would have a temperature of about 60 nanokelvins, far colder than the cosmic microwave background. But for tiny black holes, the process is much more dramatic. A black hole with the mass of a mountain would explode in a flash of gamma rays brighter than the Sun. The implications are profound. If Hawking is correct, then black holes are not the eternal prisons we once thought. They're temporary features of the universe, slowly evaporating as virtual particles carry away their mass and energy. The largest black holes will outlive the stars by countless eons, but even they will eventually fade away, leaving behind only the whisper of Hawking radiation. Virtual particles may also have played a role in the birth of the universe itself. During cosmic inflation, quantum fluctuations in the infline field created tiny variations in the density of space and time. These fluctuations were essentially virtual particles that became real as space expanded, stretching them beyond their quantum depth limit. These fossilized quantum fluctuations are imprinted on the cosmic microwave background radiation. When we look at the slight temperature variations in this ancient light, we're seeing the signature of virtual particles that existed when the universe was smaller than a proton. The galaxies, stars, and planets that exist today all trace their origins back to these primordial quantum fluctuations. In a sense, we are all children of virtual particles. The matter in our bodies was forged in stars that formed from gas clouds that condensed along the scaffolding of dark matter, which itself was shaped by the quantum fluctuations of the early universe. The carbon in our cells, the calcium in our bones, the iron in our blood, all of it can trace its ultimate origin back to the virtual particles that danced in the quantum vacuum during the first fraction of a second after the Big Bang. So the next time you touch a solid object, remember that the forces holding it together are mediated by virtual particles. The stability of matter itself depends on these ghostly quantum fluctuations that exist in the liminal space between being and non-being, between something and nothing. Imagine that the cosmic inflation that created our universe didn't just happen once and then stop. Imagine instead that it's an eternal process, constantly creating new regions of space, new universes, new realities. This is the concept of eternal inflation, and it suggests that our universe, everything we can see, from the nearest star to the most distant galaxy, might be just one bubble in an infinite cosmic foam. The idea emerges naturally from our understanding of how inflation works, how during the brief period of cosmic inflation that shaped our universe, hoarded space expanded exponentially, driven by the energy of the inflaton field. But what if this process doesn't happen uniformly everywhere? What if some regions of space stop inflating while others continue? Picture a pot of boiling water. Bubbles form and expand, but they don't all appear at the same time or grow at the same rate. Some bubbles merge with others, some pop at the surface, and new ones constantly form. Now imagine that each bubble is an entire universe, complete with its own space, time, and physical laws. This is the multiverse that eternal inflation creates. Our observable universe would be the interior of one such bubble, where inflation ended about 13.8 billion years ago, and matter and energy cooled into the structures we see today. But beyond our cosmic horizon, inflation might still be continuing, creating new bubble universes at an exponential rate. The mathematics of eternal inflation suggest that this process, once started, can never completely stop, even as some regions exit inflation and become observable universes like ours. The inflating regions expand so rapidly that they always outpace the regions where inflation has ended. Displacement, it's like trying to empty a bathtub while the faucet is turned on full blast. No matter how much water you remove, more keeps flowing in. This leads to a startling conclusion. If eternal inflation is correct, then there are infinitely many universes, and they're being created at an infinite rate. Every second, countless new universes are coming into existence, each with its own unique history and properties. But here's where it gets even more mind-bending. In an infinite multiverse, everything that can happen will happen not just once, but infinitely many times. There would be universes where the laws of physics are slightly different, where the fundamental constants have different values, where the history of cosmic evolution took completely different paths. Some of these universes would be completely hostile to life, mere too hot, too cold, too chaotic for complex structures to form. Others might be perfectly suited for life, but with slightly different physical laws that allow for forms of existence we can't even imagine. And in some universes, the laws of physics might be so different that our concepts of matter, energy, and space-time don't apply at all. The concept of eternal inflation also suggests that our universe has no beginning in the traditional sense. While our particular bubble universe began 13.8 billion years ago when inflation ended in our region, the process of inflation itself might be eternal with no starting point in time. This creates a beautiful paradox. Our universe has a definite age and history, but it exists within a larger multiverse that might be timeless. We can trace the history of our cosmic bubble back to its moment of creation, but that moment of creation is just one event in an eternal process of universe generation. The implications for our understanding of existence are profound. If eternal inflation is correct, then asking why does the universe exist becomes like asking why does this particular snowflake exist? The answer isn't about the snowflake itself, but about the atmospheric conditions that make snowflakes possible. Some versions of eternal inflation suggest that the bubble universes might occasionally collide, creating observable signatures in the cosmic microwave background. Why being observable signatures in the cosmic microwave background? These collisions would appear as circular patterns of temperature variation, like the rings created when stones are thrown into a still pond. Cosmologists have searched for these collision signatures, but so far, the evidence is inconclusive. The universe's baby picture is remarkably smooth, with only tiny fluctuations that match the predictions of single universe inflation. If bubble collisions have occurred, they've left only the faintest traces. The concept of eternal inflation also raises deep questions about the nature of probability and prediction. If everything that can happen does happen somewhere in the multiverse, then what meaning do we assign to the particular combination of events that led to our existence? Some physicists argue that eternal inflation makes the multiverse concept unfalsifiable and therefore unscientific. If we can never observe other universes directly, how can we test whether they exist? Would pursue per universe, would stray, prot. Others contend that the multiverse is a natural consequence of our best theories of cosmic inflation, and that we should take its implications seriously, even if we can't directly observe other universes. What's certain is that eternal inflation transforms our perspective on cosmic uniqueness. Our universe, with its particular laws of physics and unique history, might be just one note in an infinite cosmic symphony, one story in an endless library of possibilities, one dream in the infinite mind of an eternally creative cosmos. There's something almost magical about the way our universe seems perfectly calibrated for life. The strength of gravity, the mass of the electron, the rate of cosmic expansion. Dozens of fundamental constants appear to be fine-tuned with extraordinary precision to allow complex structures like stars, planets, and ultimately conscious beings like us to exist. This observation has led to what's called the anthropic principle, a concept that's both profound and controversial. In its simplest form, the anthropic principle suggests that we observe the universe to be life-friendly simply because we're here to observe it. It's a kind of cosmic selection bias. We can only find ourselves in a universe that's capable of producing observers. Consider the delicate balance required for stars to exist. If the strong nuclear force were just slightly weaker, protons wouldn't stick together to form atomic nuclei. If it were slightly stronger, all the hydrogen in the universe would have fused into heavier elements shortly after the Big Bang, leaving no fuel for stars. The window of possibility is remarkably narrow. Or think about the cosmological constant, the mysterious dark energy that's causing the universe's expansion to accelerate. If this constant were much larger, the universe would have expanded too rapidly for galaxies to form. If it were much smaller, the universe might have collapsed back on itself before stars could ignite. The observed value seems to be in the narrow range that allows for cosmic structure formation. The physicist Martin Rees has identified 6 fundamental numbers that appear to be essential for a universe that can support complexity. These include the ratio of the electric and gravitational forces, the nuclear efficiency that determines how much energy is released in nuclear fusion, and the number of spatial dimensions. Change any of these numbers significantly, and you get a universe that's either too simple or too chaotic to support life. This fine-tuning has led to several different interpretations. Some see it as evidence of design, the idea that the universe was intentionally created with life in mind. Others argue that it's simply a consequence of the selection effect inherent in our existence as observers. The multiverse provides a third interpretation. If eternal inflation creates infinitely many universes with different physical constants, then it's not surprising that we find ourselves in one of the rare universes where life is possible. We couldn't exist in the vast majority of universes where the constants are hostile to complexity, so we naturally observe ourselves to be in a life-friendly universe. This is sometimes called the weak anthropic principle. It doesn't claim that the universe was designed for life, but rather that the apparent fine-tuning is a consequence of observational selection. We're like lottery winners marveling at the incredible odds of our victory, forgetting that someone had to win. But there's also a strong anthropic principle that goes further, suggesting that the universe must have properties that allow consciousness to develop. This version is more controversial because it seems to give consciousness a special role in the structure of reality. The anthropic principle becomes even more intriguing when we consider the possibility that consciousness itself might play a role in the evolution of the universe. Some interpretations of quantum mechanics suggest that consciousness is necessary to collapse quantum superpositions into definite states. If this is true, then the universe might literally need observers to become fully real. This leads to what the physicist John Wheeler called the participatory universe. The idea that we're not just passive observers of reality, but active participants in its creation. In this view, the universe is not just fine-tuned for life, but life is necessary for the universe to achieve its full potential. The anthropic principle also raises questions about the nature of explanation in physics. Traditionally, physicists have looked for theories that predict the values of fundamental constants from first principles. But if we live in a multiverse where these constants vary randomly, then the anthropic principle might be the only explanation we can give for their observed values. This doesn't sit well with some physicists, who see the anthropic principle as a kind of intellectual surrender. They argue that science should strive to understand why the universe has the properties it does, not just accept that we observe them because we're here to observe. Others embrace the anthropic principle as a legitimate form of scientific reasoning. They point out that we already use anthropic reasoning in many contexts. For example, we don't wonder why Earth is at the right distance from the Sun to support life, because we understand that life developed here precisely because the conditions were suitable. The anthropic principle also connects to deep questions about the relationship between mind and cosmos. If consciousness is indeed necessary for the universe to be fully real, then our existence might not be a cosmic accident, but a cosmic necessity. We might be the universe's way of knowing itself, the cosmos awakening to its own existence. Whether you find the anthropic principle compelling or troubling, it forces us to confront fundamental questions about our place in the cosmic order. Are we fortunate accidents in a universe that's mostly hostile to life, or are we integral participants in a cosmic story that required our existence to unfold? Beyond the bubble universes of eternal inflation lies an even more extraordinary possibility. The idea that every quantum event splits reality into multiple parallel worlds, each containing a different version of history, a different version of you, a different version of everything that has ever happened or ever could happen. This is the many worlds interpretation of quantum mechanics, proposed by Hugh Everett III in 1957. It suggests that when a quantum system is measured, reality doesn't collapse into a single outcome. Instead, all possible outcomes occur, each in its own separate universe. The universe is constantly branching like an infinite tree, with each branch representing a different possible history. Imagine you're at a crossroads, trying to decide whether to turn left or right. In our everyday experience, you make a choice and follow one path. But according to the many worlds interpretation, both choices are made. Mine version of you turns left, another turns right, and both versions continue to exist in parallel universes that can never directly interact. This branching happens not just for conscious decisions, but for every quantum event in the universe. Every time a radioactive atom decays or fails to decay, every time a photon passes through a double-slit experiment, every time any quantum measurement is made, the universe splits into multiple parallel worlds. The implications are staggering. If many worlds is correct, then there are parallel universes where dinosaurs never went extinct, where you chose a different career, where Napoleon won at Waterloo, where the Library of Alexandria was never burned. Every possible variation of history exists somewhere in the vast landscape of parallel worlds. In some of these parallel universes, the differences are microscopic. Microscopic holds a single electron, taking a slightly different path through a semiconductor. In others, the differences are dramatic, entire civilizations rising and falling in patterns completely different from our own timeline. The theory suggests that there are parallel versions of you reading these words right now, but with slight differences in their experiences. Maybe in one universe, you're listening to this with headphones instead of speakers. In another, you decided to listen to this tomorrow instead of today. In yet another, you never discovered this video at all. But here's the beautiful and terrifying aspect of many worlds: fours, these parallel selves, can never communicate with each other. Each universe is isolated by the quantum decoherence that prevents different branches from interfering with each other. You can never know what choices your parallel selves made, never discover what happened in the worlds where history took a different turn. Some physicists find this interpretation elegant because it removes the mystery of quantum measurement. Instead of asking why quantum systems collapse into definite states when observed, many worlds suggests they don't collapse at all. Neither, they just split into multiple realities, each with its own definite outcome. Others find it extravagantly wasteful, requiring an infinite number of parallel universes just to explain the behavior of quantum systems. As physicist David Deutsch puts it, the multiverse is not a theory, it's a prediction of the theory, specifically the theory of quantum mechanics, taken to its logical conclusion. The many worlds interpretation also raises profound questions about identity and continuity. If you're constantly splitting into multiple versions of yourself, which one is the real you? Are you the same person who went to bed last night, or just one of many branches that emerged from that person's quantum interactions? Some philosophers argue that personal identity becomes meaningless in a many-worlds universe. Others suggest that each branch maintains its own sense of continuity and identity, even if it can't access the memories or experiences of its parallel selves. The concept of parallel worlds also appears in other areas of physics. In addition to the quantum multiverse of many worlds, there's the cosmic multiverse of eternal inflation, where different regions of space have different physical laws. There's also the possibility of parallel branes in higher dimensional space, where our entire universe might be just one membrane floating in a higher dimensional bulk. These different types of multiverse could potentially interact in complex ways. The bubble universes of eternal inflation might each contain their own quantum multiverse of parallel worlds. The parallel worlds of quantum mechanics might exist on parallel branes in higher dimensional space. The full structure of reality might be far more complex and layered than we can currently imagine. What's particularly fascinating is that these parallel worlds might not remain parallel forever. Some theories suggest that under certain extreme conditions, of perhaps near black holes or during cosmic inflation, different branches of the quantum multiverse might merge back together, creating interference patterns that could theoretically be observed. The search for evidence of parallel worlds has led to some creative experimental proposals. Scientists have suggested looking for subtle correlations in quantum experiments that might reveal the influence of parallel branches. Others have proposed that dark matter might be ordinary matter existing in parallel branches, weakly interacting with our universe through gravity. Whether or not parallel worlds exist, the concept challenges our most basic assumptions about reality. It suggests that the story of existence might be infinitely more complex than we ever imagined. To new are not just one universe with one history, but an infinite library of all possible worlds, all possible stories, all possible versions of what it means to exist. Here's a question that might make you feel slightly dizzy. What if the universe isn't made of matter and energy, but of mathematics itself? What if the equations that describe reality don't just model the universe, but actually are the universe a might of pure mathematical relationships that somehow became conscious of themselves? This isn't just philosophical speculation, it's a serious idea in modern physics, known as the mathematical universe hypothesis, proposed by cosmologist Max Tegmark. The suggestion is that our physical reality is nothing more than a mathematical structure, hologic, complex web of relationships and patterns that exists in abstract mathematical space. Think about it this way. When physicists describe the behavior of an electron, they don't really tell you what an electron is made of. Instead, they give you a set of mathematical relationships, idescavias that describe how the electron interacts with other particles, how it moves through space, how it responds to electromagnetic fields. The electron, in a sense, is nothing more than these mathematical relationships. But why stop with electrons? Perhaps atoms are mathematical structures, molecules are mathematical structures, you and I are mathematical structures. Maybe the entire universe is just mathematics playing out its own logical implications, like a cosmic computer program running on the hardware of pure abstraction. This idea has a beautiful simplicity to it. Instead of asking why the universe obeys mathematical laws, we can ask why we ever thought it was made of anything other than mathematics. The unreasonable effectiveness of mathematics in describing nature, as physicist Eugene Wigner put it, becomes perfectly reasonable if nature is mathematics. Consider the most fundamental equations in physics: Einstein's field equations, Schrödinger's equation, Maxwell's equations. These aren't just descriptions of how things behave. They might be the actual substance of reality. When we solve these equations, we're not calculating what the universe does. We're discovering what the universe is. Discovering what the universe is. The mathematical universe hypothesis also provides an elegant explanation for the fine-tuning of physical constants. If all possible mathematical structures exist as physical realities, then we naturally find ourselves in one of the mathematical structures that's complex enough to support observers like us. The other mathematical structures, the ones that don't allow for complexity or consciousness, exist as well, but they contain no observers to wonder about their existence. This connects to the concept of computable universes, mathematical structures that can be generated by finite computer programs. Some physicists speculate that the universe might be running on a kind of cosmic computer, with the laws of physics being the program and the evolution of the universe being the output. But what would it mean for mathematics to exist in this way? In our everyday experience, mathematical objects like numbers and equations seem abstract, existing only in our minds or on paper. But perhaps this is backwards. Perhaps mathematical objects are the most real things there are, and physical objects are just our way of experiencing certain mathematical relationships. The Platonic view of mathematics suggests that mathematical objects exist independently of human minds. The number pi doesn't exist because we discovered it. We discovered it because it exists. The Pythagorean theorem wasn't invented by humans. It was always true, waiting to be uncovered. If this view is correct, then mathematics has a kind of objective reality that transcends the physical world. Taking this idea further, perhaps what we call physical reality is just our particular way of experiencing a small subset of mathematical reality. We're embedded in a mathematical structure, and we experience it from the inside as space, time, matter, and energy. But from the outside, it's just pure mathematics. This has profound implications for the nature of consciousness. If we are mathematical structures, then consciousness might be what it feels like to be a certain type of mathematical computation. Our thoughts, our emotions, our sense of self-worth, all of these might be mathematical processes unfolding in the abstract space of mathematical reality. The idea also suggests that there might be forms of mathematical existence that are completely alien to our experience. Just as there are mathematical structures that don't correspond to anything in our physical world, there might be forms of consciousness and existence that arise from mathematical structures we can't even imagine. Some physicists have suggested that the universe's mathematical structure might be gradually revealing itself to us through scientific discovery. Each new equation we uncover, each new law of physics we discover, might be a glimpse into the underlying mathematical reality that constitutes our existence. The mathematical universe hypothesis also raises questions about the relationship between computation and reality. If the universe is mathematical, then perhaps it's also computational, a vast calculation, unfolding in mathematical space. The future might not be predetermined in the usual sense, but rather computed moment by moment by the mathematical structure of reality itself. This connects to the concept of digital physics, which suggests that the universe might be discrete rather than continuous at the smallest scales. Perhaps space and time are pixelated, like a cosmic computer screen, with the pixels being the fundamental units of reality. Whether or not the universe is literally made of mathematics, the mathematical universe hypothesis reminds us that the boundary between abstract and concrete, between thought and reality, might be far more fluid than we usually imagine. In the end, Perhaps the universe is dreaming itself into existence through the language of mathematics. Imagine you're adjusting the dials on a cosmic radio, trying to tune in the station that broadcasts life-supporting universe. The signal is incredibly weak, and you have to get dozens of different settings exactly right.
Hide this.
The strength of gravity, the mass of the electron, the rate of cosmic expansion, the nuclear binding energy, turn any dial just slightly, and the signal disappears into static. This is the fine-tuning problem, and it's one of the most puzzling observations in all of cosmology. The fundamental constants of nature appear to be calibrated with extraordinary precision to allow for the existence of complex structures like stars, planets, and ultimately, life itself. Let's start with the cosmological constant Mintel's, the mysterious energy that's causing the universe's expansion to accelerate. If this constant were larger by just 1 part in 10 circumflex 120, the universe would have expanded so rapidly that galaxies could never have formed. If it were smaller by the same amount, the universe would have collapsed back on itself before stars could ignite. The observed value falls in an incredibly narrow window of possibility. To put this in perspective, imagine trying to hit a target the size of a coin somewhere in the known universe. The level of precision required for the cosmological constant is like being blindfolded and not only hitting the coin, but hitting a specific atom on the coin's surface. Or consider the fine structure constant, which determines the strength of electromagnetic interactions. If this constant were just 4% different, carbon wouldn't form in stars. Without carbon, the complex chemistry that makes life possible simply couldn't exist. The window of possibility for a universe with carbon-based life is astonishingly narrow. The nuclear strong force provides another example. If it were just 2% weaker, protons wouldn't stick together to form atomic nuclei. If it were 2% stronger, all the hydrogen in the universe would have fused into heavier elements within minutes of the Big Bang, leaving no fuel for stars. Again, the observed value falls in a tiny window that allows for stellar nucleosynthesis. Ius, Loimu force and Sanitai. Even the number of spatial dimensions appears to be fine-tuned. In a universe with 2 spatial dimensions, complex structures couldn't form. In a universe with 4 or more spatial dimensions, planetary orbits would be unstable and atoms couldn't exist. 3 spatial dimensions seem to be the sweet spot for complexity. This fine-tuning extends to the early universe as well. The initial density of the universe after the Big Bang had to be incredibly close to the critical density that separates eternal expansion from eventual collapse. If the density were just slightly higher, the universe would have collapsed before stars could form. If it was slightly lower, matter would have been too diffuse for gravity to pull it together into structures. The physicist Martin Rees has identified 6 fundamental numbers that appear to be essential for a universe that can support complexity. These include the ratio of the electric and gravitational forces, the nuclear efficiency that determines how much energy is released in nuclear fusion, and the amplitude of the primordial density fluctuations that led to galaxy formation. Change any of these numbers significantly, and you get a universe that's either too simple or too chaotic to support the emergence of complex structures. The parameter space for a life-supporting universe appears to be vanishingly small compared to the vast space of possible universes. This fine-tuning has led to several different interpretations. Some see it as evidence of intelligent design, like the idea that the universe was intentionally created with life in mind. The precision required seems to exceed what we might expect from random chance. Others argue that the fine-tuning is explained by the anthropic principle. I observe the universe to be life-friendly, simply because we're here to observe it. In this view, the fine-tuning is a selection effect, rather than evidence of design. The multiverse provides another possible explanation. If eternal inflation creates infinitely many universes with different physical constants, then it's not surprising that we find ourselves in one of the rare universes where life is possible. The vast majority of universes would be lifeless, but conscious observers could only exist in the tiny fraction that happens to have life-friendly constants. Some physicists have proposed that the constants might not be constant at all, but rather dynamical variables that evolve over time or vary from place to place. In this view, we happen to live in a region of space-time where the constants have values that allow for complexity. Others have suggested that the fine-tuning might be an illusion we're sit, that life could exist in universes with very different physical laws, just in forms we can't currently imagine. Perhaps silicon-based life could exist in universes with different chemistry, or plasma-based life could exist in universes with different nuclear physics. The fine-tuning problem also raises questions about the nature of explanation in physics. If the constants are fine-tuned by chance, then perhaps there are aspects of reality that don't have deeper explanations. If they're fine-tuned by design, then we're led into metaphysical territory that's traditionally outside the realm of science. What's certain is that the fine-tuning of the universe's constants is one of the most striking features of our cosmos. Whether it's evidence of design, a consequence of selection effects, or a hint of deeper physical principles we haven't yet discovered, it reminds us that our existence depends on a delicate balance of forces and constants that could easily have been different. What if everything you've ever thought was solid and real mills, with the chair you're sitting on, the device you're listening to this on, even your own body, is actually made of something far more ethereal than matter or energy? What if the fundamental building block of reality isn't particles or fields, but information itself? This radical idea is gaining traction in physics, where researchers are discovering that information might be more fundamental than the physical objects we observe. It's a concept that would have seemed like science fiction just a few decades ago, but it's now at the forefront of theoretical physics. The idea begins with a simple observation. Every physical process can be described in terms of information processing. When an electron moves from one energy level to another, it's not just a physical event mine, it's also an information transfer. When particles interact, they're exchanging information about their properties. When you measure a quantum system, you're gaining information about its state. But perhaps this is backwards. Perhaps the information isn't just describing the physics. Perhaps the information is the physics. Maybe what we call matter and energy are just different ways that information organizes itself in the cosmic database of reality. This perspective has emerged from several different areas of physics. In quantum mechanics, the fundamental entity isn't the particle itself, but the wave function, in essentially a mathematical description of all possible information about the particle's properties. The particle's real properties don't exist until they're measured, until the information becomes actualized. Black hole physics has provided another clue. When matter falls into a black hole, it seems to disappear from our universe. But Stephen Hawking showed that information can't be destroyed. It must be preserved somehow. This led to the idea that the information about the matter might be encoded on the black hole's event horizon, like data stored on a two-dimensional surface. This insight evolved into the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. It's like a cosmic hologram, where the three-dimensional reality we experience is actually a projection from information stored on a two-dimensional surface. The implications are profound. If the holographic principle is correct, then our entire three-dimensional universe might be a projection from information encoded on a distant two-dimensional boundary. We think we're living in a 3D world, but we might actually be characters in a 2D cosmic computer program. This connects to the concept of digital physics, which suggests that the universe might be fundamentally computational. Instead of thinking of reality as made of continuous fields and particles, perhaps it's made of discrete bits of information, cosmic pixels, that can be in one state or another. In this view, the laws of physics aren't just describing how things behave. They're the algorithm that processes information in the cosmic computer. The evolution of the universe isn't just a physical process, it's a vast calculation, with each moment representing a new state in the cosmic computation. The physicist John Wheeler captured this idea with his famous phrase, "it from bit are." The suggestion that every physical quantity derives its ultimate significance from binary choices, from bits of information. In Wheeler's vision, the universe isn't just described by information, it's made of information. This information-theoretic view of reality also helps explain some of the puzzles of quantum mechanics. The uncertainty principle, for instance, can be understood as a limit on how much information can be extracted from a quantum system. The collapse of the wave function represents the moment when potential information becomes actual information. Quantum entanglement, where particles remain correlated even when separated by vast distances, can be understood as a form of information sharing, when that particles aren't sending signals to each other. They're sharing the same information in a way that transcends spatial separation. The idea that information is fundamental also appears in cosmology. The cosmic microwave background radiation, the afterglow of the Big Bang, is essentially a vast information storage system, encoding details about the early universe in the patterns of hot and cold spots across the sky. Some physicists have proposed that the universe itself might be a kind of quantum computer. The complexity we observe, from the formation of galaxies to the evolution of life, might be the result of this cosmic computation unfolding over billions of years. This perspective also raises profound questions about consciousness. If the universe is made of information, then perhaps consciousness is simply what it feels like to be a certain type of information processing system. Our thoughts, our memories, our sense of self, all of these might be patterns of information rather than activities of physical brains. The information-theoretic view of reality also suggests that the universe might have a kind of memory. Every interaction, every measurement, every quantum event leaves an information trace. The universe isn't just evolving, it's learning, accumulating information about its own states and possibilities. Whether or not reality is literally made of information, this perspective has already led to practical advances in technology. Quantum computers, quantum cryptography, and quantum sensing. Quantum computers, quantum cryptography, and quantum sensing all depend on understanding and manipulating information at the most fundamental level. In the end, the idea that information is the fundamental building block of reality offers a new way of understanding our place in the cosmos. We're not just observers of the universe, we're information processors, participating in the cosmic computation that creates and maintains the reality we experience. Long before telescopes could peer into the cosmic microwave background, long before equations could describe the curvature of space-time, human beings sat around fires under star-filled skies and wondered how it all began. Every culture that has ever existed has grappled with the mystery of creation, and the stories they told reveal a profound universal human need to understand our origins. What's remarkable is how many of these ancient creation myths contain elements that resonate with modern cosmology, not because the ancients had access to scientific instruments, but because they were asking the same fundamental questions we're still asking today, and sometimes their intuitive insights came surprisingly close to what we've discovered through science. Take the Hindu concept of cosmic cycles, described in texts thousands of years old. The universe, according to Hindu cosmology, undergoes infinite cycles of creation, preservation, and destruction. Each cycle lasts billions of years. And when one universe ends, another begins. This bears a striking resemblance to the cyclic universe models that some modern cosmologists propose, where our Big Bang might be just one episode in an eternal series of cosmic expansions and contractions. The Vedic creation hymn, the Nasadiya Sukta, contains one of the most sophisticated creation stories ever conceived. It begins with the observation that in the beginning, there was neither existence nor non-existence, neither space nor time. From this primordial void, the universe emerged through the power of cosmic heat and desire. The hymn even ends with a note of humble uncertainty, acknowledging that perhaps no one, not even the gods, truly knows how creation began. This ancient humility about ultimate origins echoes the honest uncertainty of modern physics. We can trace the universe back to fractions of a second after the Big Bang, but the moment of creation itself remains shrouded in mystery. Like the Vedic poets, we must acknowledge the limits of our understanding. The Babylonian creation epic, the Enuma Elish, describes the universe emerging from the primordial waters of chaos. The ordered cosmos is born from the defeat of Tiamat, the goddess of chaos and salt water. While this might seem purely mythological, it contains the profound insight that order emerges from disorder, that structure arises from chaos, a theme that appears in modern theories of self-organization and complexity. Norse mythology tells of the universe beginning with Ginnungagap, the yawning void between the realms of fire and ice. When the hot and cold realms met, they created the first drops of water from which all life emerged. This creative tension between opposing forces mirrors the role of symmetry breaking in modern physics, where the universe's complexity emerges from the breaking of primordial symmetries. The ancient Chinese concept of the Tao speaks of the universe emerging from the interplay of yin and yang, complementary forces that create all of reality through their dynamic interaction. This dualistic view of creation resonates with the wave-particle duality of quantum mechanics and the matter-antimatter asymmetry that allows our universe to exist. Aboriginal Australian creation stories speak of the Dreamtime, a timeless realm where ancestral spirits shaped the land through their travels and actions. Time and space emerge from this deeper, more fundamental reality. This bears a fascinating resemblance to the idea in modern physics that space and time might be emergent properties of a more fundamental quantum reality. The Hopi creation story describes the universe emerging through a series of worlds, each more complex than the last. Humanity progresses through these worlds, gaining wisdom and consciousness with each transition. This evolutionary view of creation, where complexity and consciousness emerge gradually, parallels our scientific understanding of cosmic evolution. What's particularly beautiful is how many creation stories acknowledge the role of consciousness in creation. The Egyptian god Pater speaks the world into existence through divine words. The Judeo-Christian tradition has God creating through speech. Let there be light. The Hindu tradition speaks of the universe as the dream of Brahman, where consciousness is the fundamental reality from which all else emerges. These stories anticipate, in mythological language, some of the deepest questions in modern physics about the role of observation and consciousness in quantum mechanics. They suggest that our ancestors intuited something profound about the relationship between mind and cosmos, between awareness and reality. The Polynesian creation story tells of the universe emerging from the cosmic egg, with the sky and earth separating from an initial unity. This image of the universe, beginning in a compact, unified state, and then expanding into complexity, is remarkably similar to the Big Bang model. Even the concept of nothing playing a role in creation appears in ancient traditions. The Taoist concept of Wu Wei, or creative non-action, suggests that something can emerge from nothing through the power of emptiness itself. This resonates with the quantum vacuum and the idea that our universe might have emerged from quantum fluctuations in empty space. These ancient creation stories remind us that the wonder we feel when contemplating cosmic origins is not new. It's a fundamental human experience that connects us to countless generations of our ancestors who looked up at the same stars and asked the same questions. While our methods of investigation have changed, our sense of awe and mystery remains constant. When we ask how the universe began, we're not just asking a scientific question, we're venturing into the deepest waters of philosophy, where questions about existence, causation, and meaning converge in ways that can make even the most rigorous thinker feel slightly dizzy. The fundamental question, why is there something rather than nothing, has haunted philosophers for millennia. It's a question that seems simple enough to ask, but when you really think about it, it's almost impossible to answer. After all, any answer you give presupposes the existence of something minus laws of physics, quantum fields, mathematical structures that could serve as the foundation for everything else. The 17th century philosopher Gottfried Leibniz argued that this question is the deepest of all philosophical questions. He proposed that there must be a sufficient reason for everything that exists, including the universe itself. But this leads to an infinite regress. If the universe exists because of some reason, What explains the existence of that reason? Modern cosmology has revealed that this question is even more subtle than Leibniz imagined. The quantum vacuum, as we've discovered, is not truly empty. It's filled with virtual particles and zero-point energy. So perhaps the question isn't, why is there something rather than nothing, but rather, why is there something rather than just quantum vacuum? But even this reformulation doesn't solve the puzzle. The quantum vacuum itself is governed by laws, the laws of quantum mechanics and relativity. These laws have a kind of existence, even if it's abstract. So we're back to asking why there are laws rather than no laws, why there's structure rather than no structure. The physicist Steven Weinberg once commented that the more we understand about the universe, the more pointless it seems. This observation touches on what philosophers call the is-ought problem, the gap between scientific description and human meaning. Science can tell us how the universe works, but can it tell us why it matters? Yet there's another way to look at this. Perhaps the emergence of consciousness in the universe is not accidental but inevitable. If the universe is structured in such a way that it naturally gives rise to complexity, and if complexity naturally gives rise to consciousness, then perhaps the universe's purpose is to know itself through conscious beings like us. This idea has a long philosophical pedigree. The ancient Greeks spoke of the universe as a cosmos masura, an ordered, beautiful whole. The philosopher Aristotle argued that the universe has an inherent tendency toward order and purpose. Modern science has revealed that the universe does indeed have an inherent tendency toward complexity, from the formation of atoms to the evolution of life. The anthropic principle raises its own philosophical puzzles. If we can only exist in a universe that's fine-tuned for life, then our existence provides no evidence about whether the universe was designed or whether we're just lucky. It's like trying to determine whether a lottery is fair by interviewing only the winners. But the multiverse hypothesis, if correct, might resolve this puzzle. If there are infinitely many universes with different properties, then our existence in a life-friendly universe is not surprising. It's inevitable. We're not lucky winners of a cosmic lottery. We're simply the observers who happen to exist in one of the universes where observers are possible. This has profound implications for how we think about meaning and purpose. If our universe is just one of infinitely many, does that make our existence more or less meaningful? Some find this notion deflating mindverse. If everything that can happen does happen somewhere, then nothing we do is truly unique or special. Others find it liberating. If all possibilities are realized somewhere in the multiverse, then our particular version of existence, with all its struggles and joys, its beauty and tragedy, is a unique contribution to the totality of what exists. We're not just observers of the universe, we're participants in the cosmic exploration of all possibilities. The question of consciousness adds another layer of philosophical complexity. If consciousness is fundamental to the universe, if it's needed to collapse quantum wave functions, or to give meaning to existence, then perhaps we're not just accidental byproducts of cosmic evolution. Perhaps we're the universe's way of achieving self-awareness. This connects to the ancient philosophical question of whether mind or matter is more fundamental. Materialists argue that consciousness emerges from complex arrangements of matter. Idealists argue that consciousness is primary, and matter is just how consciousness appears to itself. The strange world of quantum mechanics, with its apparent dependence on observation, has given new life to these old debates. The possibility that the universe is mathematical raises its own philosophical questions. If reality is pure mathematics, then what does this say about the nature of existence? Are we just patterns in a cosmic equation? Or does being a pattern in an equation somehow constitute a form of existence that's as real as any other? Perhaps the deepest philosophical implication of modern cosmology is that it forces us to confront the limits of human understanding. The universe might be stranger than we can imagine, operating according to principles that our minds are simply not equipped to grasp. This doesn't mean we should stop trying to understand, but it does suggest that a certain humility is appropriate when contemplating the deepest questions about existence. In the end, the question of cosmic origins brings us face to face with the mystery of existence itself. Not just the existence of the universe, but the existence of anything at all, including our own questioning minds. There's something both humbling and strangely comforting about reaching the boundaries of what the human mind can comprehend. When we venture into the deepest questions about cosmic origins, we inevitably encounter concepts that stretch our cognitive abilities to their breaking point, and perhaps beyond. Consider the simple question: what came before the Big Bang? Our minds are wired to think in terms of cause and effect, of temporal sequences, of before and after. But modern cosmology suggests that time itself began with the Big Bang. There was no before, because there was no time for a before to exist in. Yet even as we say this, we can't help but think, but what was there before time began? This isn't a failure of scientific education or philosophical sophistication. It's a collision between the evolved architecture of human cognition and the fundamental nature of reality. Our brains developed to help us navigate a world of medium-sized objects moving at moderate speeds, where time flows steadily from past to future and causes precede effects. We never evolved to understand quantum mechanics or general relativity or the birth of time itself. The philosopher Immanuel Kant argued that space and time are not features of reality itself, but rather the forms through which human minds must perceive reality. We can't perceive anything except through the lens of spatial and temporal relationships. This suggests that our most fundamental concepts, the very categories through which we experience the world, might be inadequate for understanding the deepest truths about existence. Modern neuroscience has revealed just how constrained our perceptual and cognitive abilities really are. We can see only a tiny sliver of the electromagnetic spectrum. We can directly perceive only 3 spatial dimensions, even though physics suggests there might be many more. We experience time as flowing from past to future, even though the equations of physics treat time as just another dimension, no different from space. Our mathematical abilities, while remarkable, also have limits. We can manipulate abstract symbols and follow logical rules, but we can't truly visualize or intuize higher dimensional spaces, infinite sets, or non-Euclidean geometries. We rely on mathematical formalism to guide us into territories where intuition fails. This raises profound questions about the relationship between human understanding and truth. If our minds are fundamentally limited by their evolutionary history, how can we know whether our scientific theories are approaching truth or simply constructing elaborate fictions that make sense within the constraints of human cognition? The physicist Werner Heisenberg once observed that what we observe is not nature itself, but nature exposed to our method of questioning. Perhaps the same is true of our understanding of cosmic origins. We're not discovering how the universe actually began, but rather how it began according to the questions we're capable of asking and the answers we're capable of comprehending. Yet there's something remarkable about the fact that we can recognize these limitations. A truly limited mind wouldn't be aware of its own limitations. The fact that we can conceive of concepts that exceed our understanding, mind, infinity, eternity, the birth of time itself, suggests that our minds have a kind of transcendent quality, even if they're ultimately bounded. This connects to the ancient philosophical distinction between knowledge and wisdom. Knowledge is about accumulating facts and understanding mechanisms. Wisdom is about recognizing the limits of knowledge and finding appropriate ways to live with uncertainty and mystery. The mystical traditions of many cultures have long recognized that the deepest truths about existence cannot be grasped through ordinary conceptual thinking. They point toward forms of understanding that transcend the subject-object duality of normal consciousness. This would turn dispersing to forth one vase pulled for whether such forms of understanding are legitimate ways of knowing or simply elaborate self-deceptions remains an open question. Science itself has revealed the provisional nature of human knowledge. Every scientific theory is potentially falsifiable, subject to revision in light of new evidence. The history of science is littered with theories that seemed absolutely certain at the time, but were later overturned. This suggests that our current understanding of cosmic origins, no matter how sophisticated, is also provisional. But perhaps this is not a limitation, but a strength. The willingness to hold our beliefs lightly, to remain open to new evidence and new ways of thinking, is what allows scientific understanding to progress. The recognition that our knowledge is limited is what drives us to keep questioning, keep exploring, keep pushing against the boundaries of the known. The question of cosmic origins also brings us face to face with what philosophers call the hard problem of consciousness. How does subjective experience arise from objective physical processes? Why is there something it's like to be conscious rather than just complex information processing happening in darkness? If consciousness is fundamental to the universe, if it's needed to collapse quantum wave functions or to give meaning to existence, then perhaps the limitations of human consciousness are also limitations on our understanding of reality itself. We might be like characters in a story trying to understand the nature of the author, or like fish trying to understand the nature of water. Yet despite these limitations, or perhaps because of them, the quest to understand cosmic origins remains one of humanity's most noble endeavors. It represents our refusal to accept mystery passively, our determination to push against the boundaries of the possible, our willingness to venture into territories where our minds can barely follow. In the end, the limits of human understanding might be not obstacles to overcome, but features of the landscape to appreciate, reminders that reality is far stranger and more wonderful than any mind can fully grasp. What if the Big Bang wasn't the beginning of everything, but simply the latest chapter in an eternal cosmic story? What if our universe is like a vast cosmic heartbeat, expanding and contracting in an endless rhythm that has no beginning and no end? This is the vision of the cyclic universe, an idea that's both ancient and cutting edge. Long before modern cosmology, Hindu and Buddhist traditions spoke of time as circular rather than linear, with the universe undergoing endless cycles of creation, preservation, and destruction. Each cycle, called a kalpa, lasts billions of years, and when one universe ends, another begins. Modern physics has given new life to this ancient intuition. The cyclic universe model suggests that our Big Bang was preceded by a big crunch, our collapse of a previous universe, that somehow rebounded into the expansion we observe today. Instead of the universe beginning in a singular moment of creation, it bounces eternally between expansion and contraction, like a cosmic yo-yo. The appeal of this model is obvious. It eliminates the uncomfortable singularity at the beginning of time, the moment when physics breaks down, and we can say nothing meaningful about what came before. In a cyclic universe, there is no before, because there is no beginning mean just an eternal dance of expansion and contraction. But how could such a cosmic bounce work? Classical general relativity suggests that when a universe contracts, it should collapse into a singularity. For a cyclic universe to work, something must prevent this collapse, or somehow transform it into a new expansion. One possibility involves quantum effects. Just as quantum mechanics prevents electrons from spiraling into atomic nuclei, quantum gravity might prevent the universe from collapsing into a true singularity. Instead, when the universe reaches a certain minimum size, quantum effects could cause it to bounce back into expansion. Another approach involves extra dimensions. In some string theory models, our universe is a three-dimensional brane floating in a higher dimensional space. The cyclic universe could result from collisions between branes, with each collision triggering a new Big Bang. These brane collisions could occur regularly, creating an endless cycle of universal death and rebirth. The physicist Paul Steinhardt has proposed a specific version of the cyclic model, where the universe undergoes periods of very slow contraction, followed by rapid expansion. During the contraction phase, the universe becomes smooth and flat, solving the same problems that cosmic inflation was designed to address. The Big Bang becomes not a moment of creation, but a phase transition, like water turning to steam. What's particularly elegant about cyclic models is that they could explain the arrow of time without requiring a beginning. In our current universe, time has a clear direction, entropy increases, memories are of the past, causes precede effects. But in a cyclic universe, this arrow of time might reverse during the contraction phase, creating a kind of cosmic palindrome where the universe reads the same forwards and backwards. The cyclic universe also offers a different perspective on the fine-tuning problem. Instead of asking why the constants of nature are perfectly calibrated for life, we might ask whether they evolve from cycle to cycle. Perhaps the universe is gradually tuning itself, with each cycle creating conditions slightly more favorable for complexity and consciousness. Some versions of the cyclic model suggest that information can survive the bounce from one cycle to the next. The universe might have a kind of memory, carrying forward the lessons learned in each cycle. This could explain why our universe seems so well suited for the emergence of complexity. It's not the first attempt, but the result of countless previous experiments in cosmic evolution. The observational evidence for cyclic models is still ambiguous. We would need to detect signatures of the previous universe in the cosmic microwave background radiation, or find evidence of the extra dimensions required by brain collision models. Some researchers have claimed to see patterns in the cosmic background that might be echoes of previous cycles, but these claims remain controversial. The cyclic universe also raises profound philosophical questions. If time is circular rather than linear, what does this mean for concepts like progress, purpose, and meaning? Are we doomed to repeat the same cosmic story endlessly, or does each cycle bring genuine novelty and growth? There's something both comforting and unsettling about the idea of eternal recurrence. Comforting because it suggests that existence is not a brief flicker between two voids, but an endless exploration of possibilities. Kendivan Turv Nojturia Spaldenai. Unsettling because it challenges our usual sense of linear time and unique historical moments. Bandinia Samotivda, Forfdenia Spoo, that tree. The cyclic universe also connects to deep questions about the nature of existence itself. If the universe has always existed in some form, then existence becomes a brute fact rather than something that requires explanation. We don't need to ask why there is something rather than nothing, because there has always been something. Whether or not our universe is actually cyclic, the idea reminds us that the Big Bang might not be the ultimate beginning of everything. It could be just one event in a much larger story, a story that extends infinitely into the past and future, where our particular cosmic epoch is just one verse in an endless cosmic poem. Here's an idea that might make you question the very nature of reality. What if everything you experience, every sensation, every thought, every moment of your existence, is actually a projection from information encoded on a distant two-dimensional surface? What if you're living in a cosmic hologram, and the three-dimensional world you take for granted is actually an illusion? This isn't science fiction or philosophical speculation. It's the holographic principle, one of the most profound and counterintuitive ideas in modern theoretical physics. It suggests that all the information contained in a volume of space can be encoded on its boundary, like a cosmic hologram that projects a three-dimensional reality from a two-dimensional surface. The idea began with the study of black holes, those cosmic monsters where gravity is so strong that nothing, not even light, can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. The entropy of a black hole, essentially the amount of information it contains, is proportional not to its volume, but to the area of its event horizon. This was deeply puzzling. In ordinary thermodynamics, the entropy of a system is proportional to its volume. Harder, a larger container can hold more gas molecules in more arrangements, so it has higher entropy. But black holes seem to violate this rule. Their entropy was determined by their surface area, not their volume. Stephen Hawking's work on black hole radiation deepened the puzzle. When black holes evaporate through Hawking radiation, they seem to destroy information, something that quantum mechanics says should be impossible. This led to the black hole information paradox, one of the deepest puzzles in theoretical physics. The holographic principle emerged as a potential solution. If all the information in a region of space can be encoded on its boundary, then the information falling into a black hole might not be destroyed after all. Instead, it might be encoded on the black hole's event horizon, like data stored on a cosmic hard drive. Gerard Hooft and Leonard Susskind developed this idea further, proposing that the holographic principle might apply not just to black holes, but to the entire universe. All the information in any three-dimensional region of space might be encoded on its two-dimensional boundary. The most concrete realization of this idea is the ADS-CFT correspondence, discovered by Juan Maldacena. This remarkable duality shows that a gravitational theory in a higher dimensional space can be exactly equivalent to a quantum field theory on its boundary. Chu is boundary. It's like discovering that a three-dimensional movie is actually being projected from a two-dimensional screen. In this framework, what we experience as gravity might be an emergent property of quantum information processing on a lower dimensional boundary. The curvature of space-time, the bending of light around massive objects, the expansion of the universe, Myers of Fall. All of these might be projections from a more fundamental reality that exists on a distant two-dimensional surface. This has profound implications for our understanding of reality. If the holographic principle is correct, then the solid three-dimensional world we inhabit is actually a kind of illusion. We're like characters in a video game, convinced that we're moving through a three-dimensional space when we're actually just patterns of information being processed on a two-dimensional screen. But unlike a video game, this holographic reality would be completely consistent and self-contained. You couldn't detect that you're living in a hologram by examining the world around you, because the hologram would contain all the information necessary to create a perfect three-dimensional experience. The holographic principle also suggests that the universe might be fundamentally digital rather than analog. If all the information in space can be encoded on a boundary, then there might be a minimum unit of information, the cosmic pixel, that sets the resolution of reality. Space and time might be quantized at the smallest scales, like the pixels on a computer screen. This connects to the concept of the universe as a quantum computer. If reality is holographic, then the evolution of the universe might be a vast computation, with each moment representing a new frame in the cosmic movie being projected from the boundary of space. That connects to the concept of the universe as a quantum computer. If reality is holographic, then the evolution of the universe might be a vast computation. The holographic principle also has implications for consciousness. If you are a pattern of information encoded on a two-dimensional surface, then consciousness might be what it feels like to be a certain type of information processing pattern. Your thoughts, your memories, your sense of self, mine and all. All of these might be aspects of how information is organized and processed on the cosmic hologram. Some researchers have speculated that the holographic principle might explain why the universe appears to be fine-tuned for life. If consciousness is a natural feature of information processing systems, then perhaps the universe is structured to maximize the complexity of information processing. The holographic principle also raises questions about the nature of space itself. If three-dimensional space is projected from a two-dimensional boundary, then space might not be fundamental, but rather an emergent property of more basic information processing. This could revolutionize our understanding of the Big Bang and the origin of the universe. Whether or not we actually live in a holographic universe, the principle has already transformed theoretical physics. It's shown that seemingly different theories can be exactly equivalent, that information might be more fundamental than matter or energy, and that the reality we experience might be far stranger than we ever imagined. At the heart of our cosmic origin story lies a profound mystery. We have two supremely successful theories of physics, quantum mechanics and general relativity, but they seem to be fundamentally incompatible. Quantum mechanics describes the microscopic world of atoms and particles, while general relativity describes the large-scale structure of space and time. Both theories work magnificently in their own domains, but when we try to combine them, they seem to tear each other apart. This incompatibility becomes critical when we try to understand the very first moments of the universe. In those earliest instants, the universe was both incredibly small, where quantum effects dominate, and incredibly dense, where gravitational effects dominate. To understand what happened then, we need a theory of quantum gravity. The search for this theory has been one of the great quests of modern physics, and it might hold the key to understanding not just how the universe began, but what came before the Big Bang itself. The problem is that quantum mechanics and general relativity make fundamentally different assumptions about the nature of reality. Quantum mechanics says that particles exist in superposition states until they're observed. That measurement plays a crucial role in determining reality, and that uncertainty is built into the fabric of existence. General relativity, on the other hand, describes a deterministic universe where space and time form a smooth, continuous fabric that's curved by matter and energy. When physicists try to apply quantum mechanics to gravity, they encounter infinities, mathematical expressions that blow up and become meaningless. It's as if the universe is telling us that we're asking the wrong questions or using the wrong mathematical tools. String theory represents one of the most ambitious attempts to solve this puzzle. Instead of treating particles as point-like objects, string theory suggests that the fundamental constituents of reality are tiny, vibrating strings. These strings can vibrate in different patterns, and each pattern corresponds to a different particle. What makes string theory particularly elegant is that it naturally incorporates both quantum mechanics and gravity. The graviton, the hypothetical particle that mediates gravitational force, emerges automatically from the mathematics of string theory. It's not added as an afterthought, but arises as a necessary consequence of the theory's structure. String theory also suggests that space has more dimensions than the three we experience. The extra dimensions are curled up so small that we can't perceive them directly, but they play a crucial role in determining the properties of the particles we observe. The precise way these dimensions are curled up could explain why the fundamental constants of nature have the values they do. Another approach to quantum gravity is loop quantum gravity, which takes the radical step of suggesting that space itself is quantized. Just as energy comes in discrete packets called quanta, space might come in discrete chunks at the smallest scales. Space and time might be woven from tiny loops of quantum geometry, like a cosmic fabric made of the smallest possible threads. Loop quantum gravity offers a different perspective on the Big Bang. Instead of beginning with a singularity where density becomes infinite, the universe might have begun with a quantum bounce, hydroincision from a previous contracting phase to our current expanding phase. The extreme conditions near the bounce would be regulated by quantum effects, preventing the formation of a true singularity. This could resolve one of the deepest puzzles in cosmology. What happened before the Big Bang? In loop quantum gravity, there might have been a previous universe that contracted and then bounced back into expansion. The Big Bang becomes not a moment of creation, but a moment of transition. Causal dynamical triangulation offers yet another approach, suggesting that space-time itself might be emergent from more fundamental discrete building blocks. The smooth space-time we experience might be like the smooth surface of water, which emerges from the interactions of countless discrete molecules. These quantum gravity theories also make predictions about what we might observe. String theory predicts the existence of extra dimensions and new particles that might be detectable in high-energy experiments. Loop quantum gravity predicts specific patterns in the cosmic microwave background that could reveal the quantum nature of the Big Bang. The holographic principle, which emerged from string theory, suggests that all the information in a volume of space can be encoded on its boundary. This could revolutionize our understanding of the universe's information content and how it evolved from the earliest moments. Quantum gravity might also explain the nature of dark matter and dark energy, the mysterious components that make up most of the universe. These phenomena might be manifestations of extra dimensions or quantum effects that become apparent only on cosmological scales. The search for quantum gravity is more than just an academic exercise. It's an attempt to understand the deepest level of reality, to discover the fundamental code that underlies all existence. If successful, it would give us a complete description of how the universe works from the smallest scales to the largest, from the first moments of creation to the ultimate fate of the cosmos. The theory of quantum gravity, when it finally emerges, might reveal that our universe is just one of many, that the Big Bang was just one event in a much larger story, and that reality is far stranger and more wonderful than we currently imagine. Here's a question that might keep you awake at night. if energy cannot be created or destroyed, one of the most fundamental laws of physics, then where did all the energy in the universe come from? Every star that shines, every planet that orbits, every particle that moves, every thought that crosses your mind, all of it requires energy. Yet energy conservation tells us that the total amount of energy in the universe should remain constant. This creates what seems like an impossible paradox. If the universe began with zero energy, how did it acquire the vast amounts of energy we observe today? And if it began with non-zero energy, where did that initial energy come from? The puzzle becomes even more perplexing when we consider the sheer scale of the universe's energy content. The observable universe contains roughly 10 circumflex 80 particles, each with rest mass energy, according to Einstein's E=mc². That's an almost incomprehensible amount of energy, more energy than you'd get from converting all the matter in 1 billion galaxies into pure light. But wait, there's more. The particles are also moving, which gives them kinetic energy. The universe is expanding, which represents a form of energy. There's electromagnetic radiation flooding space, from the cosmic microwave background to the light from distant stars. There's the mysterious dark energy that's accelerating the universe's expansion. When you add it all up, the total energy content of the universe is staggering. So where did it all come from? The answer might lie in one of the most counterintuitive insights in modern physics. The universe might have gotten all this energy for free, through a kind of cosmic accounting trick that doesn't violate energy conservation at all. The key insight comes from considering gravity's role as a negative energy. In classical physics, we usually think of energy as positive. It takes energy to lift an object against gravity, to heat something up, to accelerate a particle. But gravity itself carries negative energy. The gravitational binding energy of a system is negative, meaning it takes energy to separate gravitationally bound objects. Think of it this way. If you have a rock sitting on the ground, you can define its gravitational potential energy as zero. But if you dig a hole and put the rock at the bottom, its gravitational potential energy becomes negative. The deeper the hole, the more negative the energy. Now imagine this on a cosmic scale, or as matter clumps together under gravity to form stars and galaxies. The gravitational potential energy of the system becomes increasingly negative. The more structure that forms, the more negative the gravitational energy becomes. And more negative the gravitational energy becomes. This suggests a remarkable possibility. The positive energy of matter and radiation might be exactly balanced by the negative energy of gravity. If so, the total energy of the universe could be zero, even though it contains vast amounts of both positive and negative energy. This idea was first proposed by physicist Edward Tryon in 1973, who suggested that the universe might be a vacuum fluctuation, a quantum event where equal amounts of positive and negative energy spontaneously appear from nothing. Just as virtual particles can briefly appear in empty space by borrowing energy from the vacuum, the entire universe might have appeared as a quantum fluctuation that borrowed energy from nothing. The beauty of this idea is that it doesn't violate energy conservation. The total energy of the universe would still be zero, just as it was before the universe began. The universe would be the ultimate free lunch. A vast amount of positive energy balanced by an equal amount of negative energy, adding up to exactly nothing. But calculating the total energy of the universe is incredibly difficult. You'd need to know the exact distribution of matter and energy throughout space, including the contributions from dark matter and dark energy. We'd need to account for the energy stored in the expansion of space itself, and we'd need to calculate the total gravitational binding energy of all the structure in the universe. Recent estimates suggest that the total energy of the universe might indeed be very close to zero. The positive energy of matter and radiation appears to be roughly balanced by the negative energy of gravity. If this is true, then the universe's existence doesn't violate energy conservation after all. This has profound implications for our understanding of cosmic origins. If the universe's total energy is zero, then its creation doesn't require any external energy source. It could have spontaneously appeared from nothing through a quantum fluctuation without violating any conservation laws. The idea also connects to the concept of cosmic inflation. During the inflationary period, the universe's energy density remained roughly constant as space expanded. This seems to violate energy conservation. How can you create more energy by stretching space? But if the total energy of the universe is zero, then creating more positive energy through inflation is balanced by creating more negative gravitational energy. The energy conservation puzzle reminds us that the universe is far more subtle and surprising than our everyday experience suggests. What appears to be a vast explosion of energy from nothing might actually be a perfectly balanced dance between positive and negative energy, a cosmic magic trick that creates something from nothing without breaking any of the fundamental rules of physics. The concept of negative energy sounds like something from science fiction, but it's actually a crucial piece of the cosmic puzzle. To understand how the universe could emerge from nothing without violating energy conservation, we need to embrace the strange world of negative energy and the cosmic accounting that makes creation possible. In our everyday experience, energy is always positive. It takes energy to move objects, to heat things up, to power our devices. We think of energy as something you have more or less of, but never less than zero. But physics reveals that energy can indeed be negative, and this negativity is not just a mathematical curiosity. It has real, measurable effects. The most familiar example of negative energy is gravitational potential energy. When you lift a rock, you're doing work against gravity, storing positive energy in the rock's position. But if you define the rock's energy as zero when it's infinitely far away, then its energy becomes negative when it's in a gravitational field. The stronger the gravitational field, the more negative the energy becomes. This isn't just a matter of choosing a convenient reference point. The negative energy of gravity has real consequences. When two objects fall toward each other under gravity, they speed up, gaining kinetic energy. But where does this kinetic energy come from? It comes from the increasingly negative gravitational potential energy of the system. Think of it like a cosmic bank account. When matter clumps together under gravity, the account balance becomes more negative. But this negative balance is exactly offset by the positive kinetic energy of the moving matter. The total energy remains constant, but it's redistributed between positive and negative components. This gravitational negative energy scales with the size of the system. The more massive an object, the more negative its gravitational self-energy. A planet has more negative gravitational energy than a rock. A star has more negative gravitational energy than a planet. A galaxy has more negative gravitational energy than a star. Now imagine this on the scale of the entire universe, as matter clumps together to form the large-scale structure we observe. To galaxies, galaxy clusters, superclusters. The total gravitational binding energy becomes enormously negative. Some calculations suggest that this negative energy might be large enough to balance all the positive energy in the universe. But gravitational potential energy isn't the only form of negative energy. Quantum field theory reveals that even empty space has negative energy density in certain contexts. The Casimir effect, which creates an attractive force between parallel plates in a vacuum, arises from negative energy density between the plates. Virtual particles in the quantum vacuum also contribute to the energy accounting. These particle pairs borrow energy from the vacuum, exist briefly, and then annihilate to repay the borrowed energy. But in the presence of strong gravitational fields, such as near black holes, one particle from a pair might escape while the other falls in. The escaped particle represents positive energy, while the particle that falls in effectively carries negative energy into the black hole. This negative energy is what causes black holes to evaporate through Hawking radiation. As negative energy particles fall into the black hole, they reduce its mass and energy content. The black hole literally loses energy by gaining negative energy particles. The cosmic accounting becomes even more interesting when we consider the expansion of the universe. As space expands, the density of matter and radiation decreases minus the same amount of stuff is spread over a larger volume. But the total energy content of the universe doesn't decrease proportionally. Instead, new energy appears to be created as space expands. This seems to violate energy conservation, but it doesn't if we account for the negative energy associated with the expansion itself. The expansion of space can be thought of as doing work against gravity, storing negative energy in the geometric structure of space-time. The positive energy of matter and radiation is balanced by the negative energy of the expanding space. During cosmic inflation, this effect was extreme. The universe expanded by an enormous factor, creating vast amounts of positive energy in the form of matter and radiation. But this was balanced by an equal amount of negative energy stored in the gravitational field and the expansion of space itself. The cosmic accounting also explains how the universe can continue to expand forever without violating energy conservation. As the universe expands, the matter and radiation within it become increasingly diluted. In the far future, the universe will be a cold, empty place with very little positive energy. But the negative energy associated with the expansion will also approach zero, maintaining the balance. This suggests that the universe is like a cosmic zero-sum game. Every joule of positive energy is balanced by a joule of negative energy. The total energy of the universe is zero, even though it contains vast amounts of both positive and negative energy. The implications are profound. If the universe's total energy is zero, then its creation doesn't require any external energy source. It could have spontaneously appeared from nothing through a quantum fluctuation. Without violating energy conservation, the universe would be the ultimate free lunch, a vast amount of positive energy balanced by an equal amount of negative energy, adding up to exactly nothing. This cosmic accounting transforms our understanding of creation itself. The universe didn't need to borrow energy from somewhere else to come into existence. It simply rearranged the cosmic books, creating equal amounts of positive and negative energy from the zero energy state of non-existence. There's no such thing as a free lunch, goes the old saying. But the universe might be the ultimate exception to this rule. If our current understanding of physics is correct, the entire cosmos, with all its galaxies, stars, planets, and the energy that powers them, might be the most spectacular free lunch in existence. The idea that the universe could be a free lunch was first seriously proposed by physicist Alan Guth, one of the founders of cosmic inflation theory. His insight was simple but revolutionary. If the total energy of the universe is zero, then the universe could have appeared from nothing without violating any conservation laws. Think of it like a cosmic bank account that starts with a balance of zero. You can make withdrawals, positive energy, as long as you make equal deposits, negative energy. This cosmic accounting explains how the universe could have emerged from a quantum fluctuation in the vacuum. In quantum mechanics, the vacuum is not empty but filled with virtual particles that appear and disappear in pairs. These virtual particles borrow energy from the vacuum, exist briefly, and then annihilate to repay the borrowed energy. The uncertainty principle allows this borrowing as long as the energy is repaid quickly enough. But what if one of these quantum fluctuations was so large that it created not just a particle pair, but an entire universe? If the universe's total energy is zero, then such a fluctuation wouldn't need to repay any energy debt. It could persist indefinitely, growing and evolving into the cosmos we observe today. This is the free lunch universe hypothesis. Our entire cosmos might be a quantum fluctuation that got lucky. Instead of lasting for a tiny fraction of a second like most virtual particles, it persisted because its total energy was zero. The universe would be living on borrowed time, but the loan would never come due because the debt would always be exactly zero. The mathematical beauty of this idea is compelling. It suggests that the universe's existence doesn't require any external cause or creator. It could have spontaneously appeared from nothing through a random quantum event, without violating any physical laws. The universe would be its own cause, bootstrapping itself into existence through the peculiar logic of quantum mechanics. But the free lunch universe raises profound questions about the nature of existence itself. If the universe is truly a free lunch, then what determines whether such a lunch actually appears? Why did this particular quantum fluctuation occur, rather than remaining as mere possibility? Some physicists suggest that all possible free lunch universes do appear, heuris creating, a multiverse of infinite possibilities. In this view, our universe is just one of countless free lunches being served in the cosmic cafeteria. We observe this particular universe, not because it's special, but because we happen to be the customers who wandered into this particular restaurant. The free lunch universe also connects to the anthropic principle. If universes can appear randomly from nothing, then most of them would be hostile to life. The vast majority of free lunch universes would be too hot, too cold, or too chaotic to support complexity. So the free lunch universe also connects to the anthro-complexity. We observe a life-friendly universe not because it was designed for us, but because we could only evolve in one of the rare free lunches that happen to be suitable for biological evolution. The concept also has implications for the ultimate fate of the universe. If the universe began as a free lunch, will it eventually have to pay the bill? Current observations suggest that the universe will continue expanding forever, with matter and energy becoming increasingly diluted. In the far future, the universe will be a cold, empty place approaching the same zero-energy state from which it emerged. But this doesn't mean the free lunch will end. The universe will simply return to its original state of zero total energy, but spread out over an enormous volume. The lunch will be finished, but the bill will still be zero. Some speculations suggest that the free lunch universe might be cyclical. After expanding to maximum size and cooling to near absolute zero, quantum fluctuations might trigger a new phase of inflation, creating a new universe from the ashes of the old. Each cycle would be another free lunch, another spontaneous creation from nothing. The free lunch universe represents one of the most radical ideas in modern cosmology. It suggests that existence itself requires no explanation beyond the laws of quantum mechanics and the principle of energy conservation. The universe doesn't need a first cause or a creator. Mind us, it can be its own cause, creating itself from nothing through the power of quantum possibility. Whether or not the universe is truly a free lunch, the concept reminds us that reality is far stranger and more wonderful than our everyday experience suggests. In the quantum realm, the impossible becomes possible, and something can indeed come from nothing, as long as the cosmic books balance in the end. There's something mysteriously perfect about the cosmic microwave background radiation, FIRAM, the ancient light from the early universe that fills all of space. When we map this radiation across the sky, we discover that it has almost exactly the same temperature in every direction we look. This uniformity is so precise that it's been measured to within a few parts per million. At first glance, this might seem like a good thing. A uniform universe is a simple universe, and simple universes are easier to understand. But when cosmologists first discovered this uniformity, they realized it presented a profound puzzle that challenged our understanding of how the universe could have evolved from the Big Bang. The problem is this: according to standard Big Bang theory, many regions of the cosmic microwave background should never have been in contact with each other. Light travels at a finite speed, so there are limits to how far information can travel in the time since the Big Bang. These limits define what we call the cosmic horizon, the maximum distance over which different regions of space could have communicated. When we look at the cosmic microwave background, we're seeing light that was emitted when the universe was only about 380,000 years old. At that time, the universe had only existed for a relatively short period, so light could only have traveled a limited distance. This means that widely separated regions of the sky should have been completely out of contact with each other. Here's where it gets puzzling. Here, these regions were never in contact. How did they end up at exactly the same temperature? In physics, when two objects are at the same temperature, it usually means they've been in thermal equilibrium. They've exchanged energy until they reach the same temperature. But thermal equilibrium requires contact. And these regions of the universe appear to have been too far apart to have ever been in contact. It's like walking into a huge auditorium where everyone is wearing exactly the same outfit, down to the tiniest detail. If these people had never met each other or communicated in any way, how did they all end up dressed identically? The uniformity would be so improbable that you'd suspect some kind of coordination or common cause. The horizon problem becomes even more acute when we consider the precise scale of the uniformity. The cosmic microwave background shows tiny fluctuations in temperature, variations of about 0.00001 degrees. These fluctuations are remarkably consistent across the entire sky, with the same statistical properties everywhere we look. This suggests that not only did distant regions reach the same average temperature, but they also developed the same pattern of small-scale variations. Before cosmic inflation was proposed, the horizon problem seemed intractable. The standard Big Bang model simply couldn't explain how causally disconnected regions of space could have such similar properties. Some physicists suggested that the universe might have been created with these uniform initial conditions, but this felt like giving up on finding a physical explanation. The theory of cosmic inflation provided an elegant solution to the horizon problem. Inflation proposes that in the very early universe, there was a period of extremely rapid expansion. During this brief period, the universe grew by an enormous factor, at least 10 circumflex, 26 times larger. Here's the key insight. Before inflation, the regions we now observe as widely separated were actually close together. They were in thermal equilibrium, sharing the same temperature and properties. Then inflation stretched these regions apart, carrying them beyond each other's horizons. What we observe as the uniform cosmic microwave background is the stretched-out echo of what was once a small uniform region. It's like taking a photograph of a small, uniformly colored surface and then stretching it to enormous size.
The stretched image would appear uniform even though its different regions are no longer in contact. The uniformity we observe is a fossilized record of the pre-inflation equilibrium.
Inflation also explains the origin of the tiny fluctuations in the cosmic microwave background. During inflation, quantum fluctuations in the inflation field created small variations in density. These quantum fluctuations were then stretched by inflation to macroscopic scales, becoming the seeds for the formation of galaxies and large-scale structure. The horizon problem has been largely solved by inflation, but it raises new questions about the nature of the inflationary period itself. What caused inflation to begin? What determined how long it lasted? Why did inflation end when it did, allowing the universe to transition to the more familiar expansion we observe today? The precision of the cosmic microwave background also suggests that inflation was a remarkably fine-tuned process. The quantum fluctuations during inflation had to be neither too large nor too small to produce the structures we observe today. If they were too large, the universe would have collapsed into black holes. If they were too small, no structures would have formed at all. Some physicists have proposed that the horizon problem might have other solutions that don't require inflation. These alternatives include variable speed of light theories, where light traveled faster in the early universe, or scenarios where the universe contracted before it expanded, allowing distant regions to come into contact. But inflation remains the most widely accepted solution to the horizon problem. It not only explains the uniformity of the cosmic microwave background, but also makes specific predictions about the patterns of fluctuations we should observe. The remarkable agreement between these predictions and observations has made inflation one of the cornerstones of modern cosmology. Here's a humbling fact about our universe. Everything we can see, touch, or directly detect, match death. Every star, every planet, every grain of cosmic dust, every atom in your body represents less than 5% of what actually exists. The remaining 95% of the universe consists of two mysterious components that we can barely comprehend: dark matter and dark energy. This isn't just a small gap in our knowledge. We're essentially saying that we understand less than 1/20th of the universe's content. It's like trying to understand a symphony while only being able to hear the triangle part. The rest of the cosmic orchestra is playing a composition we can barely perceive. Dark matter makes up about 25% of the universe, and its existence is inferred from its gravitational effects. We can see how it bends light from distant galaxies, how it holds galaxy clusters together, and how it shapes the large-scale structure of the universe. The fade from bark and the fairy end into dade fur, yarari and ani. But we have no idea what dark matter particles actually are, despite decades of searching. The leading candidates for dark matter are exotic particles that interact only weakly with ordinary matter. They might be streaming through your body right now by the billions, but they would pass through without leaving a trace. These particles might be relics from the early universe, created in the first moments after the Big Bang, when conditions were so extreme that physics operated in ways we can barely imagine. Dark energy is even more mysterious. It makes up about 70% of the universe and appears to be causing the expansion of space itself to accelerate. This acceleration was discovered only in the 1990s, and it came as a complete surprise. Most physicists expected that gravity would eventually slow down the universe's expansion, but instead, we found that the expansion is speeding up. The nature of dark energy is one of the deepest puzzles in modern physics. It might be a property of space itself, a kind of energy that's inherent in the fabric of space-time, or it might be a field that permeates all of space, similar to the inflaton field that drove cosmic inflation. Some theories suggest it might be a sign that our understanding of gravity itself is incomplete. What makes dark matter and dark energy particularly relevant to cosmic origins is that they might have played crucial roles in the early universe. Dark matter could have been the first structure to form after the Big Bang, providing the gravitational scaffolding around which ordinary matter could later condense to form stars and galaxies. In the early universe, dark matter would have been relatively more important than it is today. While the density of ordinary matter decreases as the universe expands, dark matter's density decreases more slowly. This means that in the past, dark matter would have dominated the universe's matter content even more than it does today. Computer simulations of cosmic evolution suggest that dark matter formed a cosmic web of filaments and nodes shortly after the Big Bang. This invisible architecture provided the framework for galaxy formation. Ordinary matter fell into the gravitational wells created by dark matter, eventually forming the stars and galaxies we observe. Without dark matter, the universe would look very different. The tiny fluctuations in the cosmic microwave background radiation would not have grown into the large-scale structures we see today. There would be no galaxy clusters, no galaxies, no stars, and no planets. The universe would be a smooth, featureless expanse of expanding gas. Dark energy's role in cosmic origins is equally mysterious. If dark energy has been present since the beginning, it would have affected the universe's expansion throughout its history. During the early universe, when matter and radiation were denser, dark energy would have been relatively less important. But as the universe expanded and matter became more diluted, dark energy would have become increasingly dominant. This transition from matter-dominated to dark energy-dominated expansion occurred relatively recently in cosmic history, only about 5 billion years ago. Before then, the universe's expansion was decelerating due to the gravitational pull of matter. After the transition, dark energy took over and the expansion began to accelerate. Some theories suggest that dark energy might be related to the same field that drove cosmic inflation. If so, the accelerating expansion we observe today might be a weak echo of the inflationary period that occurred in the first fraction of a second after the Big Bang. The existence of dark matter and dark energy also raises questions about the ultimate fate of the universe. If dark energy continues to dominate, the universe will expand forever, eventually becoming a cold, empty space where galaxies are separated by vast distances. In the far future, even the atoms in our bodies will decay, leaving behind only elementary particles in an ever-expanding void. But dark energy might not be constant. Some theories suggest that it could change over time, potentially even reversing sign, and causing the universe to contract in a big crunch. Other theories propose that dark energy might be cyclic, driving repeated periods of expansion and contraction. The study of dark matter and dark energy represents one of the most active areas of research in modern cosmology. Experiments deep underground are searching for dark matter particles. Space-based telescopes are mapping the distribution of dark matter through its gravitational effects. Theorists are developing new models to explain these mysterious components of our universe. Until we understand dark matter and dark energy, our picture of cosmic origins will remain incomplete. These invisible components don't just fill the space between stars, They shape the very evolution of the universe itself, from its earliest moments to its ultimate fate. Deep within the heart of quantum mechanics lies a puzzle so fundamental that it challenges our basic understanding of reality itself. It's called the measurement problem, and it asks a deceptively simple question. When does a quantum system stop being a fuzzy cloud of possibilities and become a definite, measurable reality? In the quantum world, particles don't have definite properties until they're observed. An electron doesn't have a definite position or momentum until you measure it. A photon doesn't take a definite path through a double-slit experiment until you detect it. Instead, these particles exist in what physicists call a superposition. This might sound like abstract philosophy, but it's been confirmed in countless experiments. Quantum particles really do behave as if they're in multiple states at once. The mathematics of quantum mechanics, embodied in the Schrödinger equation, describes how these superposition states evolve over time with exquisite precision. But here's where it gets weird. The moment you try to measure a quantum system, something dramatic happens. The superposition collapses, and the particle suddenly has definite properties. It's as if the act of measurement forces the universe to choose one specific outcome from all the possibilities. This collapse is not predicted by the Schrödinger equation. In fact, it seems to violate the equation completely. The Schrödinger equation describes smooth, continuous evolution of quantum states, but measurement seems to cause a discontinuous jump, an instantaneous transition from multiple possibilities to a single reality. Erwin Schrödinger, one of the founders of quantum mechanics, was deeply troubled by this inconsistency. He illustrated the problem with his famous thought experiment involving a cat in a box. If quantum mechanics applies to all objects, then the cat should be in a superposition of alive and dead states until observed. But this seems absurd. Surely the cat is either alive or dead, regardless of whether anyone is looking. The measurement problem becomes even more puzzling when we consider what constitutes a measurement. Does it require a conscious observer, or can any interaction with the environment cause collapse? If a tree falls in a quantum forest and no one is around to hear it, does it make a sound? Does it even fall? Different interpretations of quantum mechanics offer different answers to these questions. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, simply accepts measurement as a fundamental feature of reality. According to this view, quantum systems exist in superposition until measured, and the act of measurement inevitably disturbs the system, causing collapse. The many worlds interpretation, proposed by Hugh Everett III, eliminates the measurement problem by denying that collapse ever occurs. Instead, every quantum measurement causes the universe to split into multiple branches, each containing a different outcome. The cat is both alive and dead, but in different branches of reality. The de Broglie-Bohm theory proposes that particles have definite properties all along, but they're guided by a quantum wave that we can't directly observe. This hidden variable theory makes the same predictions as standard quantum mechanics, but avoids the measurement problem by maintaining that reality is always definite. The measurement problem has profound implications for our understanding of cosmic origins. If consciousness is necessary for quantum collapse, then the early universe before conscious observers existed. Whole would have remained in a superposition of all possible states. Whole would have remained in a superposition of all possible states. The measurement problem has profound implications for our understanding of cosmic origins. The universe would have been a ghost, existing in a fuzzy combination of all possible histories until the first conscious beings evolved to observe it. Some physicists have proposed that the measurement problem might be resolved by considering the role of information. Perhaps measurement isn't about consciousness, but about the irreversible transfer of information from the quantum system to the environment. Once information about the system's state becomes entangled with the environment, the superposition effectively collapses. This connects to the concept of decoherence, where interaction with the environment causes quantum superpositions to become unstable. However, the delicate quantum coherence that allows superposition states to exist is gradually destroyed by environmental noise, causing the system to behave more classically. But decoherence doesn't completely solve the measurement problem. It explains why we don't observe macroscopic superpositions in everyday life, but it doesn't explain why measurement yields definite outcomes rather than just creating classical mixtures of possibilities. The measurement problem also raises questions about the nature of time and causality. If quantum systems exist in superposition until measured, then the past might not be definite until observed. Some interpretations suggest that the act of measurement might retroactively determine the history of the quantum system. This has led to proposals for delayed choice experiments, where the decision of how to measure a quantum system is made after the system has already supposedly made its choice. These experiments suggest that the measurement setup can influence the system's past behavior, challenging our usual notions of causality and temporal sequence. The measurement problem remains one of the deepest unsolved puzzles in physics. It challenges our understanding of reality, consciousness, and the nature of existence itself. Until we resolve it, our picture of how the universe evolved from its quantum origins will remain incomplete. Perhaps the measurement problem is telling us that our usual concepts of definite reality and objective existence are fundamentally flawed. Maybe the universe is more like a story being told than a machine following predetermined rules. And conscious observers are not just reading the story, but actively participating in its creation. There's a particular kind of beauty in standing at the edge of human knowledge, looking out into the vast unknown, and feeling not frustration or disappointment, but wonder in our quest to understand how the universe began. We've discovered something remarkable. The questions we can't answer are often more profound and beautiful than the ones we can. Think about what we've learned in our journey together tonight. We've explored the quantum vacuum that isn't empty, the Big Bang that wasn't a bang, the inflation that happened faster than light, the possibility that we're living in a hologram projected from a distant boundary. Each answer we've found has revealed new questions, deeper mysteries, more subtle puzzles about the nature of existence itself. This isn't a failure of science. It's science working exactly as it should. Every time we solve one puzzle, we uncover new layers of complexity, new realms of possibility that we never imagined before. The universe is like a cosmic onion. With each layer we peel away, revealing another layer beneath, more intricate and surprising than the last. Consider the measurement problem in quantum mechanics. We can predict with extraordinary precision what will happen when we measure a quantum system, but we have no idea why or how the measurement causes the system to collapse from multiple possibilities into a single reality. This gap in our understanding isn't a small technical detail. Mind you, it's a fundamental mystery about the nature of reality itself. Or think about dark matter and dark energy, which together make up 95% of the universe. We can map their effects with exquisite precision, but we have almost no idea what they actually are. We're like astronomers trying to understand the night sky while being able to see only one star in 20. The vast majority of the cosmic symphony is playing in frequencies we can't even hear. If you can't even hear, for savant indurnitain, these mysteries aren't obstacles to overcome, but invitations to wonder. They remind us that the universe is far stranger and more beautiful than our current understanding suggests. They point toward depths of reality that we're only beginning to glimpse, territories of knowledge that await future explorers. There's something deeply human about this relationship with mystery. We're the creatures who ask why and how and what if. We're the universe's way of questioning itself, of wondering about its own nature and origins. Our ignorance isn't a bug in the cosmic code. It's a feature, driving us to explore, to discover, to push against the boundaries of the known. The history of science is filled with examples of mysteries that once seemed insurmountable, but eventually yielded to human curiosity and ingenuity. The nature of light, the structure of the atom, the mechanism of heredity, the age of the earth Nucerodis, all were once profound mysteries that challenged the greatest minds of their time. Today's impossible questions may be tomorrow's textbook answers. But some mysteries may be permanent features of the landscape of knowledge. The question of why there is something rather than nothing may be unanswerable, not because we lack the right tools or theories, but because the question itself reaches beyond the boundaries of what any finite mind can comprehend. This doesn't make the question worthless. More, looks quite the opposite. Questions that push us to the limits of understanding serve a crucial role in keeping us humble, curious, and open to possibility. They remind us that we're part of something vastly larger than ourselves, something that exceeds our capacity to fully grasp or control. The mystery of cosmic origins also connects us to every human who has ever looked up at the night sky and wondered. Ancient astronomers, medieval scholars, modern physicists, we're all part of the same human quest to understand our place in the cosmos. The questions we're asking are fundamentally the same questions that have driven human curiosity for millennia. What's particularly beautiful is that embracing mystery doesn't mean giving up on understanding. Instead, it means holding our current knowledge lightly, remaining open to new possibilities, and finding joy in the process of discovery rather than just in the answers we uncover. The cosmologist Alan Lightman has written about what he calls the accidental universe, the possibility that our universe is just one of many, with no special significance or purpose. But even if this is true, it doesn't diminish the wonder of our existence. If anything, it makes our existence more remarkable, not less. We're the arrangement of atoms that became conscious, the stellar dust that learned to ask questions about its own origins. We're the universe's way of looking back at itself and feeling amazement. Even if we're accidents in a vast cosmic multiverse, we're extraordinary accidents, perhaps the most extraordinary thing that has ever happened in this particular corner of reality. The mystery of cosmic origins teaches us that wonder is not a stepping stone to knowledge, but a destination in itself. The feeling of awe we experience when contemplating the birth of time, the emergence of space, the dance of quantum possibilities. This wonder is not a temporary state to be overcome by understanding. It's a fundamental aspect of what it means to be conscious beings in a universe that's far more strange and beautiful than we can imagine. There's something deeply poetic about the story of cosmic origins, something that transcends the mathematical equations and observational data to touch the very heart of what it means to be human. The universe's beginning reads like the most ambitious poem ever written, with metaphors that span from the quantum to the cosmic, from the mathematical to the mystical. Consider the language we use to describe the early universe. We speak of the cosmic dawn, the first light, the moment when the universe became transparent. We talk about the music of the spheres encoded in the cosmic microwave background, the symphony of creation still echoing through space after nearly 14 billion years. These aren't just poetic flourishes. They're necessary because the reality we're describing pushes language to its limits. The story of cosmic inflation reads like a creation myth written by the universe itself. In the beginning, there was a field of pure potential. This field underwent a phase transition, and in that transition, space itself began to expand exponentially. The universe grew from smaller than a proton to larger than a grapefruit in a time shorter than the blink of an eye. It's a story of transformation so dramatic that it challenges our ability to comprehend it. But what makes this story particularly poetic is that it's not just about the universe, it's about us. The quantum fluctuations that occurred during inflation, fluctuations so tiny that they seem insignificant, eventually grew into the galaxies and stars that light up our night sky. The universe didn't just create space and time, it created the conditions that would eventually give rise to complexity, to life, to consciousness, to the capacity for wonder itself. We are made of star stuff, as Carl Sagan famously said. But the poetry goes deeper than that. We are made of quantum fluctuations, of virtual particles that became real, of mathematical relationships that somehow learned to feel and think and dream. We are the universe's way of composing poetry about itself. The uncertainty principle, which seems like a technical detail of quantum mechanics, becomes a poetic statement about the fundamental nature of reality. The universe cannot be pinned down, cannot be fully measured or completely understood. There's always an element of mystery, of possibility, of creative potential that exceeds our grasp. Reality is not a fixed sculpture, but an ongoing improvisation. The concept of the multiverse adds another layer of poetic complexity. If eternal inflation is correct, then our universe is just one verse in an infinite cosmic poem. Each bubble universe is a different stanza, exploring different possibilities, different ways of being. We're not just reading the poem while living inside one of its verses, experiencing it from the inside as it unfolds. The holographic principle suggests that reality might be a kind of cosmic literature, with all the information in three-dimensional space encoded on a two-dimensional surface. We might be characters in a story being told on the boundary of the universe, experiencing the narrative as reality itself. The line between metaphor and physics becomes beautifully blurred. Even the mathematics of cosmic origins has a poetic quality. The equations that describe the early universe are not just computational tools, but expressions of deep symmetries and relationships that govern existence itself. E = mx is not just a formula, but a statement about the convertibility of matter and energy, about the fundamental unity underlying apparent diversity. The fine-tuning of the universe's constants creates like a carefully crafted poem, where every word, every pause, every rhythm has been chosen with exquisite precision. Change even one fundamental constant by a tiny amount, and the entire poem collapses into meaninglessness. The universe is written in a language so precise that it allows for the emergence of languages themselves. The arrow of time gives the cosmic story its narrative structure, from the initial low-entropy state of the Big Bang to the increasing complexity of cosmic evolution. The universe has a plot, a direction, a sense of development. It's not a random sequence of events, but a story with beginning, middle, and perhaps an ending we can barely imagine. But perhaps the most poetic aspect of cosmic origins is the role of consciousness in the story. We are not just observers of the cosmic drama, but participants in it. Our ability to understand, to wonder, to find beauty in the mathematical structure of reality. This might be the universe's greatest achievement, the moment when the cosmos becomes conscious of itself. The anthropic principle, whether we interpret it as evidence of design or selection, reminds us that we're part of the story being told. We couldn't exist in most possible universes, yet here we are, contemplating our own existence. We're the universe's way of asking questions about itself, of finding meaning in the apparent meaninglessness of vast space and time. The poetry of cosmic origins also lies in what we don't know. The questions that remain unanswered: what came before the Big Bang? What is the nature of consciousness? Why there is something rather than nothing? These mysteries are not flaws in the cosmic poem, but integral parts of its beauty. They're the spaces between the words, the pauses that give meaning to the sounds. In the end, the story of cosmic origins is not just about how the universe began, but about how anything at all can begin, how possibility becomes actuality, how potential becomes real. It's a story we're still writing, still discovering, still living. We are both the authors and the characters in this cosmic poem, simultaneously creating and experiencing the ongoing epic of existence itself. As we reach the end of our journey through the mystery of cosmic origins, it's worth pausing to consider something remarkable. You are here, listening to these words, contemplating the deepest questions about existence itself. This simple fact that conscious beings like us exist in a universe that began from quantum fluctuations nearly 14 billion years ago is perhaps the most extraordinary part of the entire story. Think about the chain of events that led to this moment.
It began with a quantum fluctuation in a field we can barely comprehend, in a time before time had meaning.
This fluctuation grew into cosmic inflation, stretching the fabric of space itself beyond all recognition. The energy of inflation decayed into the fundamental particles and forces that govern our universe. Gravity began its patient work, pulling matter together into the first stars. These stellar furnaces forged the heavier elements in their cores, then scattered them into space when they died. New generations of stars formed from this enriched material, and around some of these stars, planets coalesced from the cosmic dust. On at least one of these planets, our Earth conditions were just right for a new kind of complexity to emerge. Simple molecules began to reproduce and evolve, eventually becoming the intricate dance of DNA and proteins that we call life. Over billions of years, this life diversified and complexified, eventually producing nervous systems capable of processing information about the world. And then in what might be the most remarkable development in cosmic history, some of these nervous systems became conscious. They began to ask questions about their own existence, to wonder about their place in the cosmos, to develop the tools of science and mathematics that could probe the deepest mysteries of reality. This is where you come into the story. You are not just an observer of cosmic evolution, you are its culmination, at least in this corner of the universe. You are the way the universe has developed to understand itself, to ask questions about its own origins, to feel wonder at its own existence. Your consciousness is not separate from the cosmic story, it's an integral part of it. The same quantum fields that drove inflation are present in every atom of your body. The same fundamental forces that shaped the early universe are at work in every cell of your brain. You are not just in the universe, you are the universe, organized in such a way that it can think about itself. This perspective transforms our understanding of human significance. We're not insignificant specks in a vast, indifferent cosmos. We're the moment when the cosmos wakes up and begins to contemplate itself. We're the universe's way of developing self-awareness, of asking why it exists, of finding meaning in its own existence. Here, the anthropic principle takes on new meaning from this perspective. We don't just happen to observe a universe that's suitable for life, we're the reason the universe can be observed at all. Without conscious observers, the universe would be like a symphony played to an empty concert hall. We're not just the audience, we're the universe's way of listening to its own music. But our place in the cosmic story is not just about observation and understanding. We're also active participants in the ongoing evolution of complexity. Through our science and technology, we're extending the reach of consciousness beyond the boundaries of our planet. We're beginning to understand our own genetic code, to manipulate matter at the atomic level, to search for life elsewhere in the universe. In a sense, we're the universe learning to engineer itself through us. The cosmos is developing the ability to direct its own evolution consciously. We're not just products of cosmic evolution, we're becoming agents of it. This role comes with profound responsibility. As the universe's way of understanding itself, we bear the burden of making sense of existence, of finding meaning in the apparent meaninglessness of vast space and time. We're the storytellers of the cosmos, the ones who weave the raw facts of physics and astronomy into narratives that can give meaning to existence. But we're also inheritors of a cosmic heritage that stretches back to the very beginning of time. The carbon in our bodies was forged in the cores of dying stars. The oxygen we breathe was created in stellar furnaces. The calcium in our bones was scattered into space by supernova. We are literally made of ancient starlight, walking star stuff that has somehow learned to wonder about its own origins. For me, still Iciphitin Sperius, with distaventarius distabold of the doth gen exporive and send formade enemy. We are litrius distabold of the doth and 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 all. Our place in the cosmic story is still being written. Holby, we don't know how the story will end, or even if it will have an ending in any meaningful sense. We don't know if we're the only conscious beings in the universe, or if consciousness is a common feature of cosmic evolution. We don't know if we'll eventually understand the deepest mysteries of existence, or if some questions will forever remain beyond our grasp. What we do know is that we're here, now, in this extraordinary moment, when the universe has developed the capacity to ask questions about itself. We're living in the age when the cosmos first opened its eyes and began to see itself clearly. We're part of the universe's awakening to its own existence. This is our place in the story, not as passive observers, but as active participants in the ongoing adventure of cosmic self-discovery. We're the universe's way of celebrating its own existence, of finding beauty in its own complexity, of asking questions that push against the boundaries of the knowable. And perhaps that's enough. Perhaps our role is not to solve all the mysteries, but to keep asking the questions, to maintain the sense of wonder that drives the cosmic story forward, to be the universe's way of marveling at itself. In the end, we are both the question and the answer, the mystery and the revelation, the universe discovering itself through the miracle of consciousness. And so we've traveled together through the deepest mystery of all, how everything began from what might have been nothing. We've glimpsed quantum fluctuations dancing in empty space, witnessed the birth of time itself, and contemplated the possibility that we're living in a cosmic hologram. Perhaps these ideas have shifted something in how you see your place in this strange and beautiful universe. But I have to ask, are you still awake? Because if you are, I'm slightly concerned that I may have accidentally created the world's most stimulating bedtime story. That wasn't the plan at all. Here's a simple question for you. What surprised you most about our cosmic journey tonight? If you found yourself enjoying this gentle exploration of the universe's deepest mysteries, always consider giving this video a thumbs up. It helps other curious souls discover this quiet corner of the internet, where we can wonder together about the big questions without having to solve them all at once. May your dreams be filled with quantum possibilities and cosmic horizons. Sleep well, fellow traveler. The universe will still be here in the morning, mysterious and beautiful as ever.